Also, I want to bring my bag.
Another part according to you.
Yeah.
Yes.
Sorry.
Can you say something? Press the microphone.
So which one?
And,
Oh.
okay, it works.
Does it work?
Yeah.
Okay.
Prompt me if I'm not switching. If I need to switch to
Yeah,
the
sure.
other.
Yeah. Okay. Do you think I should get it started already? You all set?
You're also.
Okay. So hi everyone. Welcome to another Safari Live seminar. This time we have it hybrid. Some people are online and some people are here with Poulami and I in this meeting room. So I'm going to introduce the speaker. Poulami Das is a PhD candidate at Georgia Institute of Technology. Her research focuses on developing compiler optimizations and software techniques to improve fidelity of near-term quantum applications, as well as designing architecture and system-level solutions for enabling fault-tolerant quantum computing in the future. Poulami obtained her master's degree from the University of Texas at Austin and bachelor's degree from National Institute of Technology, Dargapur. She is the recipient of Microsoft Research Ph.D. Fellowship, Institute Gold Medals at NIT Dargapur, and has been selected as a rising star in EECS. Her research has been recognized with the Best Research Award at the Design Automation Conference PhD Forum, Cleaver Award for the most outstanding PhD dissertation proposal in Electrical and Computer Engineering Department, Georgia Tech, and Best Paper Award at Computing Frontiers, and has appeared in top architecture and system venues like Micro, HPC, and ASP+. So, Poulami, now the stage is yours, and we look forward to your talk.
Thank you for the introduction, and I'm very glad to be here in person. So today I'll be talking about some of my recent works, and the focus of them are primarily building software and architecture for reliable quantum computing. So why quantum computing? Quantum computers promise computational advantages or promise that they can accelerate a certain class of many critical applications. For example, if you want to simulate molecules or you want to factor large numbers, if you look at these problems, these are just not possible to solve in a reasonable amount of time on conventional systems. And this exponential speed up from quantum computers is what makes them promising, because they can fundamentally change what is computable. Now, few basics of quantum computing before we move on to the later half. First of all, unlike classical bits, which stores information in the form of zeros or ones, which is used in most conventional systems, quantum computers actually store information in qubits or a quantum bit and leverage quantum mechanical properties to actually provide that exponential speed up. For instance, if you think of a qubit, it can be thought of as a point on this sphere. Any point on this sphere is a valid state for the quantum bit. Qubits can actually therefore simultaneously be in a superposition of its basis states 0 and 1. As you can see here, alpha is the probability that the qubit is in state 0, beta is the probability that the qubit is in state 1. And what you do is in quantum algorithms, you basically rotate the qubit along the sphere and you change the state. What is more important is that quantum computers leverage this entanglement property, which allows you to create highly correlated states. For instance, if you see the state of a 2-qubit system is shown here. And if you actually apply a gate on any one of the qubits, you can see the other changing as well. And this is what helps you to get a massive source of parallelism and speed up. With a linear increase in the number of qubits, you can actually get this exponential state space, which is what leads to the source of computational advantage. Because let's say you have a 50 qubit system, you are simultaneously operating on that entire 2 to the power 50 exponential state space. And quantum algorithms eventually leverage these two properties to give you speed up. Usually, you use quantum gates to manipulate the state of the qubits such that you amplify the probabilities of the correct states or the correct outcomes, so that when you measure those qubits, they will collapse to that state, which will probably be the right answer. So if you want to solve a problem on a quantum computer, you encode the problem, you initialize your qubits, and then you apply different gates. The purpose of these gates is to manipulate those quantum states such that you amplify the correct answers, as I mentioned earlier, and then you measure them and then obtain the final outcome. So a typical quantum circuit looks something like this. Here you have 2 qubits, let's say, which are initialized to the state 0, and then you apply different gates. The edge gate is a single qubit gate which operates on only one of the qubits. The other gate that you see here is a 2 qubit operation or a controlled CNOT operation that allows you to actually entangle the qubits, which is the property that you are trying to use. And then finally, once you do your computations, you measure the qubits. So this is little background about how quantum computers get their computational advantages by using these properties of quantum bits. Any questions so far before I move on? This was a little bit of background. No, very good. So quantum computing is very exciting at this moment because you can actually go and run a quantum program on a real quantum computer. We actually have quantum computers with about 100 plus qubits available to us today, which we can access through different cloud providers. And these machines are actually expected to scale very rapidly. For example, IBM has promised us that they will be able to deliver 1,000 plus qubit machine by the end of the next year. So this is very exciting. But one of the key challenges with quantum computers is noise. These devices are very, very susceptible to noise, and therefore the devices have very high error rates. Now, typically, let's say you have errors in computations. What do? You think about protecting the information, right? So you have a similar notion even in quantum. You can protect quantum information by using quantum error correction. The idea of quantum error correction is that you encode a logical qubit by using several physical qubits. So you introduce this redundancy to sort of protect against errors. And the idea is that the logical qubit will have lower error rate than your actual physical qubits. But what's the level of redundancy required? Well, something in the order of 20 to 1000x. Now this brings us to a problem. You are probably going to get a few thousands of qubits or a few hundreds of qubits in the near term. But if you need this level of redundancy, running applications in a fully fault-tolerant manner is almost impractical. Because think about it, if you have a 1000 qubit system, you need 1000 qubits to build one fault-tolerant logical qubit. It's not very good use of it. So more recently, there is this alternate paradigm that has evolved called the noisy intermediate scale quantum computing. And the idea is that you are dealing with systems with few hundreds or thousands of qubits. These are called NISK devices. And you know you cannot have fault tolerance. You cannot really run fully fault-tolerant quantum computing on these devices. You know errors will happen, and you sort of learn to live with them. So long story short, hardware errors is one of the most limiting factors that actually prevents us from running most practical quantum applications on these devices today. And let's look at the different challenges as these quantum systems grow in size. For example, back in 2019 and early 2020, Google actually announced their quantum supremacy device and their quantum supremacy experiments results. What they did is they took a 53 qubit quantum machine, and what they showed is that for certain random or arbitrary artificial tasks, they were able to outperform the most powerful supercomputer. So that has accelerated the field a lot. And what we look forward to in the near future, in the next few years, is that you will use those NISK devices where you know you can't have fault tolerance, you are running applications in the presence of noise, but you will still be able to use them for certain domain-specific applications such as VQE or QAOA. These are some specific chemistry problems. These are some specific optimization problems. For example, you do vehicular routing, you do traveling salesman's problem using QAOA. At the same time, what you want to also do is understand quantum error correction using these devices so that you can actually build those large fault-tolerant systems in the future that can actually help you run a wider class of quantum applications. For example, one of the poster child applications for that is Shor's algorithm, which is used to break basically cryptographic protocols by factorizing large numbers very quickly. Or you do Grover search for searching databases, chemistry applications again. Now, if you look at it more carefully, the reliability challenges differ. For example, when you are running applications in the NISK era, you want to develop error mitigation techniques, which will suppress the impact of errors on the computations. At the same time, you want to have systems that can help you understand quantum error correction on a smaller scale, such that you can actually build those large fault-tolerant quantum computers in the long run. And the challenge in those computers is that you want to be able to accurately identify errors very quickly, and you must be able to do it at a large scale where you have a few thousands of logical qubits. So if you look at the whole quantum computing roadmap, there are applications or algorithms that have been developing for a lot of time, and the devices are also improving. And what my work focuses on is essentially developing software or compiler solutions and architecture solutions to bridge this gap between the applications and the noisy devices. And I have proposed several compiler optimizations and software error mitigation techniques to aid the NISK applications, as well as I've come up with different architecture and system level solutions to help you understand quantum error correction and to also understand how can you build those large fault-tolerant quantum computers in future. Today, in the interest of time, I'll pick up three different works which actually cater to those three different buckets, and I'll talk about some of them. So the first thing that I'll talk about is JigSaw, which focuses on measurement error mitigation in the NISK era. But before we dive deeper into that, let's understand what does the whole NISK computing model look like a bit more closely. Suppose you want to execute this program on a quantum computer. The circuit looks like that. Let's say you want to run this on this NISK device with just 4 qubits. The first thing that you need to do is introduce a NISK compiler. The job of the NISK compiler is to take in the program qubits and map them onto the physical qubits of your device. Once that is done, it will translate the instructions that are preferably written in high-level languages to machine-compliant instructions that can be actually executed on the hardware. For instance, if you look at IBM devices, your CNOT operations will get mapped to a CX gate that can be run on IBM hardware. That gate can be different for Google devices or Rigetti machines. Right? So this is the role of a compiler. And then once you have obtained a quantum executable, you execute it on the machine. Yes.
So my question is this instruction set, is it standardized now or is it different from device to device?
Very good question. It differs from, yeah. Yes, okay. So the question was that does this ISA that we compile to, is there any standard or is there a specific thing about devices? There is sort of no standard, but one of the most widely used one is the Qiskit ISA, the one from IBM. But definitely the gates actually differ between hardware. So for example, the way you realize a 2-qubit operation on an IBM device is different from, let's say, how you realize it on a Rigetti machine or Google machine. So your compiler has to be aware of that. So you feed it into the compiler and it compiles.
So how much let's say, changes you can expect from the compiler to, let's say, just develop for IBM, and if I want to port it for Google, So how much change is basically you can expect?
So very good question. I think broadly, these are the same. They still support a few single qubit gates and a few 2-qubit operations. But again, you need to compile them differently. So you probably will use the same level of optimizations, but the final instructions will be different.
Thanks.
Any questions? Okay. Yeah. 1 second, it is not showing.
So my address is that. Which one is it?
You just described that is different. Maybe the company. So what exactly? Metrics that we have in production. Providing that IBM doesn't provide, for example, in for architecture, for example, much more reliable. Can you explain it?
Yeah, so the question was about what is different, right? So usually the way you build the qubits, they differ, and how you control them are different. And the way, although, for example, IBM is building superconducting qubits, which is same as Google broadly, but the way you actually control those devices are different. And that's why the kind of gates that are supported are different. And broadly, again, as I mentioned, you will have a similar set of universal gates. For example, you will have some 2-qubit gates, some single qubit gates that are supported, but then they tend to differ, and how you compile them to functionally identical quantum executable will be different. And the main reason is because of the difference in how you actually implement the hardware operations. You actually have, let's say, microwave resonators that you need to tune in and you need to control. So that logic is different between how Google is doing things versus how IBM does things. Or example, how Honeywell does things. Honeywell has a completely different style of designing quantum computers. They use trapped ion systems where you actually use lasers, and the challenges are different over there.
Starting to the question, basically, for example, in the normal architecture, what we have, different to one target, different metric. Right, one companies also have different metrics, so they're implementing different, and this different implementation, how they affect the end result. For example, does, for example, the Google architecture achieve more in terms of speed, the IBM more in terms of security, or it's just different implementations and there is actually no, how can I say, side effects in the end results?
So the question was about what is the difference in the end result. Yes. So frankly speaking, I think broadly the style, the way they connect the qubits is what differs, and the way they build the qubits differ. And the two companies have two different roadmaps that they are trying to achieve. IBM is trying to scale the systems in a different way compared to Google. Now, talking about end result, it's sort of basically it's like multiple people betting on the same, on different versions of the same technology, or maybe different technologies, and in the end someone will evolve as the winner, and someone might be still evolving as the winner but much later. In terms of speed, there's a difference in terms of obviously technology. For instance, if you look at systems from IBM or Google, the idea is that they use superconducting devices, so computations can happen much faster than, let's say, on a trapped ion system from Honeywell or IonQ. But at the same time, they have different challenges. For example, it's hard to scale up the Honeywell systems. If you look at devices from IBM, for example, there's a rapid progression. When I started my PhD, 1 year into my PhD, I was working with IBM 5-qubit devices. Today, I have access to a 127 qubit device. But if I look back at, let's say, Honeywell or IonQ, the roadmap is slightly different and the systems are scaling at a slower rate. So eventually, the idea is about which of these devices will be able to run real-world applications with higher fidelity. So right now, I don't think there's a clear winner yet, but obviously, just to give you some perspective, think about it. Google demonstrated their supremacy experiments on a 53 qubit quantum computer. To the best of my knowledge, there is no such study even on a 127 qubit machine from IBM. Again, I don't want it to get into trouble, but you see the difference.
Thanks, Ron.
Yeah. Any more questions before I proceed?
Quantum gates are they?
You can use them for questions. Yeah.
Receiver. And
Yeah.
Okay.
So eventually this workers on Poulami. Maybe we can just do that. I will bring it next to you, and then I will bring it to the person that wants to ask the question.
Okay.
And then go over there.
Do you need me to do anything or no?
Just that you keep the speaker
Switching
as-
thing.
Could you repeat the question?
Yes. So the question was about how are these gates different from, one second, I don't know if I switched it. Can you?
Yeah, it should be with the speaker or with the microphone place, right?
Yeah, Mike will always.
Just select your mic. Yeah.
Maybe.
Yeah. So the question was, how are these gates different from, let's say, traditional gates? And is it possible to build different types of gates? Typically, vendors will try to provide you a minimalist set of gates. And the reason for that is once you want to actually do those gate operations on your device, you need to do a lot of calibration experiments to understand and fine tune the knobs to perform those actual gates in reality. Let's say, think about it this way, when you do a 2 qubit operation, you're actually sending signals down the resonators, you are letting them interfere. So to do that stuff, you need to actually have very, very good control parameters that will be least sensitive to noise. And because of that, there is a huge calibration overhead. For instance, it can take several hours. When I was doing my first set of experiments, early phase of my PhD, even on those small machines, IBM would be calibrating for a few hours overnight. So that is what is a bit challenging, because now you want to scale up, and if you want to support a lot of gates, then this becomes hard because your system is basically down, it's not usable. So that's a challenge, which is why they support a minimalist gate where you do entanglement operations and you support some software gates or some hardware single qubit gates. And the flip side to that is if you have multiple 2 qubit, which they call native gates, if you have multiple of them, there's an advantage. There are things that you can do better. For example, it can reduce the crosstalk in certain architectures, and a lot of companies are also evaluating that front. For example, if you look at Rigetti machines today, they are effectively supporting, in most cases, 3 different 2 qubit native gates. So it's obviously a richer ISA, but at the same time, it has calibration overheads. Yes.
Let me shout. So this calibrating, how should I imagine this? Is this overhead like once every time you start a new program? Is it if you add a new gate to your hardware somehow? When do you need to calibrate?
That's a very good question. It depends. Okay, like most engineering answers. Typically, the device provider or the cloud provider takes care of it for you, and they give you the bunch of the data. There are techniques to sort of overlap this calibration so that you reduce the system downtime. For instance, there was a paper from Google and they call it the snake optimizer. And the idea is that you do a full scale system level calibration at once and then keep on locally calibrating so that if there is a drift in those parameters, you sort of go and detect it because these parameters change very quickly. They're very sensitive. So then you do some localized calibrations. In most cases, what can happen is that these machines are usually operated inside a fridge. And so once you warm up, cool down, you want to recalibrate your entire device again. And sometimes systems can be down for a long, long time for that. They're probably also running some device level experiments because a lot of times what happens is these machines are also used for studying machines. So that aspect is also there. On top of that, let's say I'm a person who is building the next set of compiler optimizations. So sometimes I may or may not rely fully on the calibration data because I think it is stale. So I may quickly go and recalibrate something on my own to check how confident I am on the device parameters that's provided by the cloud provider, let's say. So it depends. Where the answer is clear enough. Good. Should I proceed forward? Okay. Where was I? Yeah, so you execute the whole quantum executable that your compiler has given you. Now the challenge is you can have different types of errors, and let's see what types of errors can happen. So let's say you are doing that gate operation. Okay. Oh God. Yeah, let's say you're doing that gate operation on those 2 qubits. They are vulnerable to errors. Okay, so you can have a gate error. At the end of your program, you want to actually measure the qubits, and those measurements can be vulnerable to errors too. Sometimes your qubits actually lose information even if they are not doing anything. So it's remaining idle and it's not doing anything. It's bound to, accumulate some errors. Because think about it this way, right? Those quantum states, each of them is a valid state on that sphere. And even if you have the slightest perturbation, you end up in a different state. So what happens from the high level perspective? Well, you get a different result. For example, if you look at the correct output of this program, it's supposed to be 1, 1. Whereas what you might get is 0, 1. So it's incorrect. So in the NISK model, what you do is you repeatedly execute the executable for several trials. And each time you might get a different output. And what you do is you draw a probability distribution for all the outputs that you have logged on for so long. And then you try to infer the results from this output distribution. For instance, a very easy trick here could be that let's pick the peak of the histogram as the correct answer, which you will be able to detect in this case. And as you can see here, besides the correct answers, due to errors, you're bound to get incorrect results. Okay, and then the idea of NISK model is essentially to use this noisy histogram to sort of still do better than your best known classical algorithm. In fact, sometimes what can happen is that one of these particular outcomes can appear very frequently, almost as frequent as your correct answer. And that's because of correlated errors. In the interest of time, I will be focusing mostly on measurement errors today because they tend to be the dominant source of errors. But as you can see, quantum programs, they are vulnerable to different types of errors. For those of you who are interested, I listed down some of my previous works in the other slide, and they basically target the other types of errors. For example, Foresight deals with gate errors, Adapt deals with how you can mitigate idle errors, Hammer tries to mitigate correlated errors, and what I'll describe is JigSaw, which I'll talk about is its focuses on mitigating measurement errors. Question?
Yeah, sorry again.
Shout.
I will shout again. So in the absence of such errors, would quantum computing be deterministic?
Oh,
So it depends on the application. For instance, if you run this circuit, it will always give you 1, 1. Because what that X gate does is it does a bit flip. So if your state of qubit 0 is 0, it flips to a 1. When 1 controls the qubit 1 in state 0, it will flip qubit 1. No errors, you will get 1, 1 all the time. But let's say instead of that X gate, I had a Hadamard gate. Hadamard gate actually creates a superposition state. So 50% of the time, you will get a 0, 50% of the time a 1. Now you use that information to control the second qubit. When you control with 0, if the other qubit is in state 0, output will be 0 for the other qubit. If the control is 1, other qubit is in state 0, there's a control not, so it will become 1, 1. So now if you look at the output, it will be either a 0, 0 or 1, 1 with equal probabilities. So again, it depends on the application.
One question, so the distribution is rated on time, on their own. The distribution that we mentioned in the slides.
This one,
Yeah,
it's a noisy distribution in this case.
so when it's rated, when the application is running.
So yes, so you repeatedly execute, let's say for 1,000 trials, and then you draw this distribution.
For each micro operation.
No, for the entire executable.
Okay.
Okay, so you get, let's say, an executable with 100 operations. You run all of it, you get an outcome. Okay, you log it. You do the second trial, you do the third trial, and so on. Once you have realized your trials are over, now you do the distribution. Okay.
So what are the trends in, let's say, occurrences of these errors, and how are the device level optimizations addressing these over time? So I assume that there are various works, such as many of the works we've conducted, focusing on the architecture side and also software side to mitigate or correct these errors. So my question is that how are the device trends going, let's say, in the physics optimizations?
So yes, those of you who are interested can look at a device graph on first paper that I wrote. It was on multiprogramming. I was very disappointed, frankly speaking, when I was writing that paper because the error rates were quite high. Now I feel very confident because there is a clear improvement in the device error rates. But at the same time, what you can do with software is essentially squeeze out a lot more performance. So gate errors, let's talk about them. They are currently in the ballpark of, let's say, 0.5 to 1%, depending on the device technology again. Measurement errors, average, I would say it's 4%. Depending on the device, it can be higher, it can be lower. Idle errors, typically what you would see a lot of these blogs which says, oh, these qubits can retain their information for only 10 microseconds, 100 microseconds. So which is what comes in this bucket. How long can you retain the information? That is also increasing, but again, depends on the devices. Usually, if you take a closer look at most of these systems, you will see a huge variation. One of the qubits might have 200 microseconds of coherence time. One of them will have 20 microseconds. So that is where you can do more intelligent software to sort of take into account of those factors. And those variations exist even for gate errors, measurement errors as well. Correlated errors, you just see it in the output of the output distribution. There's a factor of measurement errors and idle errors that contribute to it, but it's a bit more complicated than that. But long story short, there is clear improvement in the device error rates, and I hope it continues. But at the same time, with software, you can obviously squeeze more performance out of them. So, any more questions? So let's move on. So let's talk a little more about measurement errors. Why are they so crucial? The error rates are really high. And the issue is that even if your entire computation doesn't encounter any other error, all of these remain error-free. When you measure the qubits at the end to retrieve the final computational outcome, it's wrong. And this becomes a problem because if you look at some of the error rates on most of these existing devices, as you can see here, I think this is a 27 qubit device from IBM. This is a really good machine. It has very low error rates compared to others. And as you can see here, the measurement error rates are almost more than 3 times the average 2-qubit gate error rates. And 2-qubit gates are very error prone as well. And if you look in the worst case, you have a very high error rate over there. Why this becomes a bit problematic when you grow your program sizes is because if you look at the way computations happen, every time you perform your computations and your trial is about to get over, you want to measure your qubits, you measure all program qubits. And this becomes challenging because now all your measurements must remain error-free so that you can get a correct outcome. Even if one of the measurements fail, the probability of which is quite high because of the high error rates, you get an incorrect outcome. And therefore, as you grow the program size, the probability to encounter measurement errors increases. And this is because measurement errors are the dominant sources of errors on most of these NISQ systems.
These error rates that increase because of, let's say, increased number of qubits, how much of them do you envision, or like, do you know that can be mitigated by physical, let's say, isolations, or like, let's say, either distancing or like materials that would kind of like isolate them better, or is it possible?
This has a problem.
It's much more noisy than the point.
So the question was about improving measurement error rates at the device level. I wouldn't say they are not improving. They are improving, but the pace is much slower. And in many cases, it's just hard to understand the source of the errors and mitigate them. And this has to do with the fact that in most cases, you are actually sharing some of the resonators that leads to crosstalk, or you are actually dealing with a lot of components, analog and digital devices, amplifiers, that are spread out across different thermal domains. So there's an element of thermal noise. And that's what introduces errors in this whole process. It's a slow process. In most cases, measurements are the slowest operation on quantum devices. And therefore, during that time, your qubits can decohere as well. So as a result, because of these challenges, it's actually hard to completely eliminate it at the device level. It's an open problem. Device people are also working, software people are also working.
But what is there is any need for like designing like able for the solution, for example, some kind of hybrid implementation? People look on both the device and software and try to create a solution that's not distant from each other. For example, there's sometimes that the hardware people are working completely unaware of the software, and the software people are working completely unaware of the hardware. My question is, that people working in the intersection of both to try to design more hybrid solutions?
Yes and no. For example, for me, it's very hard to get hold of a device guy from IBM just like that, right? Sometimes companies are very, very super sensitive. In many cases, they won't even leak how they do these measurement operations. So there is an element of that. But at the same time, I would imagine like there is a lot of work going on internally in those companies where they talk to each other and develop solutions for sure. Yeah. Yes.
So, if you as a researcher cannot access these state-of-the-art machines, then what?
I can access the machines. I just do not have full transparency into what they do for all aspects.
Okay.
So they will not leak a lot of information. And that's why probably you go and do internships at IBM and Google and Amazon.
So now that we're interrupted, I just want to tell the Zoom folks, if they have questions, please let us know also. Either put in chat or just ask it. And
I can see a couple of things in chat, but I don't want to mess it up. So maybe.
okay, yeah. No, they were just about the audio levels.
Okay, okay.
If there are questions, I will.
Yeah, but I think measurement is one of the most error-prone operation. A lot of times you just don't have enough transparency into it simply because they are trying to protect it. They might be actively working on it, right? So that there's an element of that. But in many cases, a lot of the times what you do is you devise. There is not, I wouldn't say it's completely disjoint, right? You will see a lot of papers from IBM where they show that, this is what our device level improvement is giving us. And then we are building the software that takes it a little further, kind of things. Okay, should I proceed? Okay, now the even bigger problem with measurement errors is that when you measure a lot of qubits, these instruments, they interfere a lot with each other, creating crosstalk. And because of crosstalk, your effective measurement error rate actually increases. So let's say you're measuring a qubit in isolation, it has a certain error rate. But when you measure multiple qubits together, which is what you would typically do in the program, let's say you have a 4-qubit program, your computations are over, now you measure them. In that case, because of crosstalk, the effective error rate can increase. For instance, if you look at the measurement error rates on Google Sycamore, you see a clear difference in the average and worst case error rates in isolated measurements versus simultaneous measurements. So this is another issue, is that when you run large programs, you become a lot more vulnerable to crosstalk. So then, if you look at some prior works on measurement error mitigation using software, let's talk about one of these key approaches from IBM. So let's say we want to mitigate measurement errors when you run this program on this toy 2-qubit quantum computer. Well, think about it this way. Before you measure, so IBM follows a matrix-based approach. So the key intuition is that before you measure the qubits, there are only 4 possible states they can be in, right? Either one of those 4. So what the method does is it goes and prepares those qubits in those states and measures them. No computation, it's just a profiling or calibration phase where you prepare all those 4 basis states, you measure them. Now you can measure them correctly or as when any one of the other remaining states, right? So then what you do is prepare this matrix. So for instance, if you look at the diagonals, that's the probability that you prepare a certain state and you measure it correctly. Whereas the other entries in the matrix correspond to the state you prepared it in and then you measured it incorrectly. And once you build that probability distribution, you can sort of reverse engineer the correct state based on the outputs that your program gives you. For instance, let's say you run this program now. You have that matrix, you can actually correct. And let's say the correct answer in this case is 1, 1. After you have corrected the histogram or the output distribution using the noise matrix, your probability of success increases from 50 to 70%, let's say. There's a downside to this. First of all, it requires a very large number of calibration circuits because you have to do a calibration for the exponential number of states. It's limiting in some sense because you need to do this post-processing using this very large matrix, which has an exponential state space, and that becomes a problem. So it has some limited applicability. So there was another work on measurement error mitigation, which uses the notion that you can transform the state. And it was called Flip and Measure. It was by Swamit who was at my lab, and it appeared in Micro 2019. The idea was that your measurement error depends on the state. So if your qubit is in state 1, you're more likely to encounter an error than your qubit being in state 0. So if you use that insight, you can actually, let's say in this case, you're supposed to measure a 1, 1 if your computations are correct. So what you do is you introduce those X gates that flip the 1 ones back to 0, 0. Now, if you measure the qubits, you are likely to get a cleaner distribution because you have reduced the vulnerability to measurement errors. Of course, you don't know the program output, so the paper mentions some clever ways in how you want to flip each of those qubits. But one of the key things that you look at both these approaches, which are quite standard now, is that they still rely on measuring all the qubits for doing their error mitigation. And that still does not eliminate the fundamental bottleneck that we are trying to address, that in large programs, you'll be vulnerable to crosstalk and your effective error rate can increase. So that becomes a challenge because they rely on measuring all qubits. So we started off with the insight that, if your goal is to reduce measurement errors, which grows as your program size grows, why not measure fewer qubits and then try to sort of reconstruct your distribution? To give you an example, let's take the previous circuit I was talking about. If you run that circuit on an ideal setting where there is no noise, the circuit is ideally supposed to produce a 1-1 output all the time. So instead of running this one circuit, what you do is you run two different circuits. The computations in both circuits are identical if you look at them, but what differs between them is that now you measure fewer qubits in each copy, and they're different. So in the first copy of the program, you're actually measuring qubit 1. In the second copy of the program, you're measuring qubit 0. Now, let's say you run them, you will actually get these partial or marginal probability distributions. We are good at tensor products, we do it. Well, we get the correct answer. This is very good. So partial measurements or circuits with partial measurements can actually help you attain higher fidelity information. But then the question is, are they alone sufficient? Let's take a different example this time. I briefly mentioned this circuit before. The Hadamard gate is the H gate, which prepares your qubit in an equal superposition state. So at the end of the Hadamard gate, qubit 0 is in a superposition of 0 and 1. And once you do the second C0 operation effectively, you get a 0, 0 or 1, 1 with equal probabilities. So this is what the output distribution should ideally look like. And this is, again, without any noise. Let's just consider the ideal scenario. We take a similar approach again. We prepare two copies of the circuit where the computations are identical, but in each copy you measure a different set of qubits. Again, you run them on a machine, let's say, and then you try to do the tensor product. Well, now we have a problem. We are not able to recreate the output distribution. And why this happens is because, well, we don't know the correlation. The reason quantum computers are so powerful is that the quantum algorithms operate on highly correlated states. So you cannot completely eliminate that, and you need that correlation to figure out the correct outcome. And so ideally, we want correlation as well as high fidelity, and we should optimize for both. That brings me to our solution, JigSaw. So we proposed JigSaw and it appeared in Micro 2021. And the idea was that, let's say you have a program, take the program, for 50% of your trials, run the entire program as is. We call it the global mode. What this gives you is a very noisy histogram. The output is bound to have low fidelity because it has more measurement operations. But what this gives you is all the correlated outcomes that you will see if you run the program. Now, in addition to that, we have these CPM or circuits with partial measurements. The idea is again similar to what I described earlier. You do your computations, but now you measure only a subset of qubits in each copy. More importantly, if you actually look at most current devices, I think I briefly mentioned it earlier during a question, they have a huge variability in device error rates. Some devices are more error prone than others. Now that you have fewer qubits to measure, you can actually recompile those programs to do those measurements on very good qubits, which has lower measurement error rates. And this is called the subset mode. And you take those additional circuits with partial measurements and you run them for the remaining 50% of the trials. Now you get very high fidelity marginal information about those qubit subsets. And then what you do is you perform Bayesian updates and sort of try to correct the global distribution that you had obtained by running the actual program. And this way, JigSaw essentially is able to capture the full correlation by running the original program. It is able to get higher fidelity by running those circuits with partial measurements. And effectively, it does give you a much cleaner distribution by combining the benefits of both. In fact, you don't have to just stick to a default subset size of 2, which we are using in our study. You can actually develop a more unique set of circuits with partial measurements by playing around with the subset sizes. And then you do a better, you can basically do an enhanced version, which is way more effective by using these heterogeneous CPM. And if you look at the impact of JigSaw, the figure here shows the relative program success rate. So program success rate is the probability that you correctly identified the output. So it's basically the probability of obtaining the correct outputs. So let's say you have executed a program for 1,000 trials, 500 times you get the correct output. So your program success rate is 50%. That's a usual way you benchmark your quantum programs on today's systems. You want to get higher success rate. So higher is better. And the baseline is basically the state of the art from IBM, the noise adaptive compilers. And what you see here is that on average, JigSaw is able to improve your success rate by 3x, in the best case up to 8x. And it's able to outperform those two prior works that I talked about, the matrix-based approach or flip and measure. What we saw also is that you can actually make this technique even more effective if you combine the benefits of all those three different optimizations, and you can combine them for greater effectiveness. So that's about JigSaw. Any questions before I switch to other topics? Yes.
So I have a.
Do I need to switch this?
No, it's fine.
Okay.
I can hear myself.
Okay. Okay.
Over there, I have a question about the program success rate. So how do we know if the output is correct in the first place?
Okay.
Yeah, I don't know if that's kind of a stupid question.
Oh, no. Absolutely not. Yes. So if you look at the size of the programs today that we can run are very small, you can simulate them on your classical machines, your conventional laptop. So you know what is the program output by default. And then you get a noisy distribution, you compare the two and you tell, okay, this.
So what would be the way in the future that the programs become so challenging to run on conventional systems?
Very good question. That was one of the problems Google faced when they did their supremacy experiments. We don't know, but the idea is that if you you will get noisy outputs, and that's why people are focused, at least in the near term, where you can't simulate them. You focus on kind of applications that can tolerate some level of noise. For example, if you're solving a traveling salesman's problem, you have a baseline solution. Your quantum computer gives you a solution. You have a way to evaluate whether the solution from the quantum computer was good or bad. This is an open problem. Yeah. But I hope this remains an open problem.
Is it possible to, let's say, for smaller problem size, let's try to understand the correlation between the true output and the noisy output that we're getting from the quantum computer? As long as we can execute this smaller problem sizes in traditional computers. Right?
Yes, yes.
If they show that the divergence between the actual the true output and the noisy output shows some sort of, let's say, correlation, right? Then can we say that, okay, though that correlation should also exist the more we increase the problem size, so that at least we don't have to compute the true output to correct ourselves from the
So the thing is this, right? Noise is random fairly. Okay. You may have some correlated errors, but broadly speaking, noise is random. Your noise for one application will differ from the noise you see in the other application. Your distributions are much cleaner when you look at smaller programs, and they tend to become more and more noisy. So if you look at the entropy of the distributions, you see it's becoming worse, and sometimes it's bad. But the idea is that even then, think about a problem. If you have, let's say, 100 qubit problem, classically, you have 2 power 100 possibilities, right? It's still very hard to deal with. So if you run your quantum computer for 1,000,000 times, you will still get at least at max 1,000,000 outcomes, which you can sort of try to play around with. Hopefully one of them will be the correct answer.
Can you use machine learning, let's say for small, for bigger problems,
To do what?
to basically detect like some noise patterns so that you can do better operation?
So there is there's a line of work, it's called Clifford data regression. And the idea is that you try to learn the probability distribution of the noise in your system by using Clifford circuits. So that means I have to explain what is Clifford circuits. No, that's fine. If you have quantum operations, you can classify quantum operations into 2 categories, Clifford and non-Clifford. Clifford operations, you can effectively simulate them on traditional machines. It is a non-Clifford operations that gives quantum computers their advantage. But what this method of Clifford data regression does is it effectively uses Clifford circuits. So you can simulate them, you learn their output, and then you sort of try to train a model where you try to learn the noise distribution and then sort of do some like analysis of how you can try to understand the noise in an unknown circuit. So that in some sense is machine learning. I think it's still an open problem. I think there are definitely going to be works on that front.
But how do you train, for example, that model? The different workloads doesn't affect, for example, the prediction of the model, for example.
So you use a bunch of, you use a very large training data set and hope it will work. Unfortunately, the Clifford data regression, it's a relatively new study and just a few years old, and therefore like it's still contained to small circuits as a proof of concept.
So, original question was actually on the 2 slides back. So I guess the JigSaw name came from the fact that we are tiling the original problems into smaller jigsaws, right? And then we are trying to recompile those jigsaws and this partial measurements are coming.
Yeah, so partial is sort of, so the idea it came from is that you have a reference picture which is not very clean, and you are using the partial measurement to draw a better
my
picture.
question is that, so is there any theoretical bound that how much size of that jigsaw would be? Let's say, do you start with the 4x4 grid with the original, so let's say if your program has, let's say, 4 outputs, right?
Here are 16 outputs
Okay.
possible.
So, yeah, so you have like 4 ends on the left side, right, on the original program.
Yes.
And then you started with, let's say, 2 ends on 2 jigsaws, each having 2 ends, right? So it's like the like halving the original circuit in some sense, right? So let's say if I start with let's say 10,000 ends, right? So did I have to start with, let's say, each individual jigsaw with 5,000 ends, or we can start with any arbitrary, or let's say how small we can go?
So the idea behind using a subset size of 2 was exactly that you do fewest measurements. So you are the most reliable, you have the most flexibility to sort of get them mapped to good qubits. And so that was the advantage we were looking at. So you have a noisy distribution already for 10,000 qubits. Now you want better fidelity. These are optimized for fidelity. So go down to fewer qubits, right? That gives you more flexibility to reduce crosstalk and also compile them such that you can measure them on the best qubits. Then the question is then how many such CPM should we design? What we saw, we have some study in the paper. The idea was that as long as you are able to get enough good quality partial information, you will be fine. We did some study and we saw that after a certain point, once you have captured sufficient high fidelity partial information about each qubit, you are sort of better off, like there are diminishing returns from additional.
So you start from partial circuits with 2 qubits,
Yeah.
and then you build upwards till you enough confidence that
Yeah.
Is it possible to perform multiple measurements in a sequential manner to get more score?
Good question. So do you do your measurements sequentially so that you don't have this problem? You can do your measurements sequentially, then you have another problem. Your qubits can decoder because let's say you are each of these measurements on IBM devices take you 4 microseconds. Your qubits don't have data retention capability beyond a few microseconds. So that's a problem. But there are still devices where you do these multiplex measurements because otherwise there is a problem. You have to use individual resonators for all of these measurements. So that becomes very hard to deal with. So devices such as Sycamore uses multiplex measurements. So that's why if you look at their simultaneous error rates, it's much higher. Any more questions before I proceed? Go ahead.
I want to go back to the program success rate again. So,
Sorry.
yeah, so here, I'm assuming like there's a 4 outcome problem, like two qubits, let's say.
Okay.
And this is the program success rate of that algorithm. And that would be the case that the correct output is, let's say the encoding is 0, 0.
Your output is supposed to be 0, 0.
Supposed to be 0, 0.
Okay.
But I only get that result 2%.
Yes.
So
It's
basically,
worse. You can see a completely. Yes. I highly encourage you to read the paper Hammer, where we saw that if you at certain points, you will see a completely incorrect outcome appearing more frequently
yeah,
than the correct outcome. So, it's like, let's say you have a 20 qubit machine, you're running a 4 qubit problem, you're fine. 5 qubit problem, you're still fine. 6 qubit problem, maybe 8 qubit problem, you're getting a different thing. But that's why I think that's what makes a lot of sense to design these optimizations so that you can push the boundary. In fact, I really like the word hammer. Did I mention that? It actually uses the information that your incorrect outcomes are not really always useless. Don't just look at the probabilities of each outcomes. Try to form clusters and neighborhoods and use that information to sort of rectify your distribution. So then you can basically, instead of relying on the distribution, the probability distribution alone, what you're doing is you're trying to create this Hamming relationships, because it's very possible you had 1 bit flip due to measurement error or 2 bit flips here and there due to a coherence error. So then, although you get this very dominant incorrect answer, it's still probably very close to the correct answer in Hamming space. So can you exploit that relationship to build your intuition about what's the correct answer? That's exactly what Hammer does. It's really one of my favorite works. Yes. Any questions?
So does this mean that if we encode the program, not in a traditional binary way, but let's say in Hamming binary way, is it better for?
You sort of you initialize your qubit so that you encode the state of the qubits that will encode your problem. And then usually so there was I think lecture or talk from Scott Aronson. When you don't know anything to do with quantum circuit, just apply all Hadamard's. But yeah, what happens if you look at most quantum circuits, you will see that you apply a lot of Hadamard's, and that's not because you're trying to be funny, but it's because you start off with an equal superposition state. Your gates are supposed to take you closely to the state that's more likely the correct outcome. So the encoding, this is a problem me and my advisor thought for some time, but never really had the time to work on it.
So like let's say that we traditionally know 0, 1, 2, 3 to be encoded as 0, 0, 0, 1, 1, 0, 1, right? If I change that, and I'm going to the Hamming space as you say, right?
So yes, so what we do is we take the distribution and form a Hamming neighborhood structure. So we form a graph from the distribution.
so your
And you look at Hamming distance after the fact, you're not encoding.
You're not encoding. Yes, yes. You're trying to learn from the Hamming structure of
I'm
the
saying
distribution.
I'm just like thinking out loud. So is it beneficial in some way that if you start with Hamming space itself, right? So if I let my program, the hardware run on Hamming.
So you get the Hamming structure because of errors behaving a certain way, right? Your program by default is not supposed to behave that way. You are still trying to start off from an all superposition state probably, where you don't know what the answer is. And you're trying to narrow down basically your search space. Yes.
How important is this metric program success rates to extract the correct answers? Because in another paper or so another metric called
Inference strength. Yeah. So program success rate tries to tell you what's the probability that you got the correct answer. What inference strength does is it tells you the probability. It's a ratio between the probability of the correct answer to the probability of the most dominant incorrect answer. And what that tells you is how good is your quality of the distribution. It's like signal to noise ratio, right? And it's basically trying to tell you how better can you infer the correct answer. So if your most incorrect answer, the most dominant incorrect answer appears with a higher frequency than your correct outcome, then your IST or the inference strength will be lower. So I think a couple of things, right? In general, this is again an open area of research. Program success rate or probability of successful trial came out, I think, 2019 as PLOS, and then we are working with it since then. There are a couple of new metrics we have introduced, such as sometimes quantum computers will actually give you a distribution as an output. You can't really take in this kind of metric or inference strength in that case. So if you look at some of our recent papers, not just mine or from our group, some papers from the other groups as well, you will see they compare the Hellinger's distance or Kale divergence between the distributions. So that sort of captures how close you are to the ideal distribution. IST is one, the inference strength that you mentioned, that sort of captures this concept of signal to noise ratio. There are some application specific metrics as well, like approximation ratio gap and stuff like that for specific applications like QAOA or VQE kind of things. Yes. But again, I think there are problems in all metrics, frankly speaking, but these are the best ones that we have so far. For example, when you look at larger programs, I myself feel distance-based metrics become very insensitive to the changes because your distribution is so large. So then what metric do we use? I don't know. It's an open problem.
Regarding the metrics, would execution time in this case would be a relevant metric at all? For example, how fast these corrections or detections happen across different mechanisms?
So usually, first of all, most of the methods or software optimizations that you develop today, typically the optimization takes a few minutes or at max half an hour. You don't want to probably build a compiler that takes you 2 days to compile. But then apart from that, I think as long as you are doing things in a reasonable time, you're good. Because I think, think about it this way. You compile in 30 seconds and get complete garbage from your quantum computer. You take 30 minutes, but get a reasonable answer from your quantum computer. I think you will choose the latter one. So, because here I think, and this is what a lot of compilers people ask me, that you're building quantum compilers, how is it different from what we do? And my answer to them is exactly this, that you optimize for total execution time. You want to shorten the program execution time. I also want to do that, first of all, but that's because I want to improve the reliability. And I will not only look for my compiler time, but I'll also look for ways to improve the fidelity of the programs when they run. Any more questions before we move on? Think.
Just clarification on what execution time means. do I have to envision a quantum program as a program code executed as in CPU, or more like a circuit on the FPGA?
It's more advanced than that. So first of all, you don't have quantum computers like your laptop. You need to access through a cloud provider. Depending on the cloud provider, you might have to reserve your device, or you're fine to just stay in their queue and let it run whenever it runs. So there's a latency, right, on that. So you compile in 30 minutes, but you're waiting in the queue for 6 hours. Now comes the time when your compiled code is essentially then just used to control qubits, right? So they load in some control instructions on an FPGA, which is the most common platform used to control qubits today. You use that and then sort of control the qubits, and then you repeatedly run that for several trials. That takes about a few milliseconds or few seconds, depending on the technology. So superconducting devices such as IBM or Google will run your program within a few milliseconds or so on. But if you look at trapped ion systems, they are longer, they take longer to run. But what you can see is that the actual execution time on the quantum hardware is still lower than your classical counterparts. In most cases, such as QAOA or VQE, the type of applications which are very useful for the NISQ era, you actually don't run your computation just once. You are basically, those problems are mapped into a parametric quantum circuit, and you run them in a hybrid manner. So you run the circuit, you do some evaluations, and then go change your circuit. You change the rotation by, let's say, a few degrees. You run it again, and you do this again and again. And so it's called a hybrid model of, or variational quantum algorithms or hybrid quantum algorithms. So again, long story short, it depends on what you're running and things like that. Does that answer the question? It depends. Okay, tell me more.
What's to open for me is let's say there's a quantum program. So you say, for example, the lifetime of is a few microseconds, right?
Yes.
So if I have let's say a program of more gates, does
Yes.
it take more, like, does it at that single program run level, that single measurement iteration level, whatever, does it take longer if I have more gates in there?
Yes, and that's why in NISQ paradigm, you want to do your computations with fewest gates possible. So if my coherence time is 10 microsecond and I throw in like maybe 10,000 operations, they will just not give me the correct value. It's garbage, right? So that's another thing, and that's what a lot of like optimizations try to do. How do you reduce the computational window so that you finish them as quickly as you can?
Is there any correlation between the speed of the gates and the number of elements?
Good question. There is probably not a lot of open data about it, but I have probably stalked some of the IBM machines for some time. And it depends, but at least for some of the machines that existed 2-3 years back, I realized if you do very slow gates, so there is a fine window basically. If your gates are too slow, you're increasing the chance of decoherence, right? So effectively, you're going to make errors. So there's a fine window. And if you have too short gates, the coupling may not be very accurate. And so the gates will be error prone. So they sort of try to maintain a balance. On an average, I think on IBM devices, 400 nanoseconds is the latency of a 2-qubit gate. Sometimes it is lower, up to 300, 350. And 4 microsecond is a measurement latency.
What's the key factor that limit the time of say the qubit, for example, right? There is a limitation when the errors are appearing on any kind of transformation that we happens. So why we have such a limitation? Why cannot store them for longer than
to be able to compute in,
You can do error correction, and that's what happens in error correction. You try to expand the boundary, you retain the information for longer. So what happens is errors still happen, you go and correct it. But then there is a challenge on that front that you don't have sufficient redundancy to do it fully fault tolerant. Yeah. There are other challenges in error correction for sure. I will talk about them, but let's clean up the NISK part before that.
But can you do it without the technology fundamentally?
I think they're trying to improve the devices. So think about it fundamentally, right? If you want to isolate your qubits a lot, it becomes a problem also, because you also need the qubits to react when you apply gate operations or measurement operations. So that is something very hard. You are basically operating on two ends of a seesaw. There are definitely a lot of works on device level for sure. They're trying to develop filtering techniques. They're trying to sort of reduce all those quasi-particle population, things like that. Sometimes a lot of the error sources you just don't understand. And it's true. In fact, there was some study in one of the devices lab from Google, and they figured out there was a two-level system effect from some random quasi-particles that they didn't even exist would happen, and that was causing a lot of errors. In fact, some of the cosmic rays can cause errors that you had not provisioned for before. So it's just, the field across the stack is evolving. That's how I like to think about it. People are developing better algorithms. You will see a new blog once in a while that says, oh, we can do this on a quantum computer better. So that stack is evolving. Devices, of course, are evolving. Every time IBM throws a new device on their cloud, there's this blog post telling you how it is way better than the previous version, but which means that front is also improving. And so we are kind of stuck in this situation where we are the compiler and architecture folks trying to sort of pace ourselves to those improvements.
Thanks.
Any other questions?
Is there any characterizations for the measurement errors?
Lot. Yeah.
What is the major contributor to these measurement errors? With crosstalk or
Crosstalk is one of them. Yeah. There are a lot of things. Sometimes you get the raw data. In fact, I was working on it for some time. I am probably still working on it, but effectively all you get is a raw signal, and in the sense IQ values, right? You then run a software discriminator to classify your qubit. Can you improve the discrimination accuracy? And those kinds of things. Those are again software problems. And I was working on it for some time. Yeah. Any more questions before we move on?
Yeah, the last one. So it's like a normal computer. When you compile once and execute forever, or you need to compile every time and execute.
Good question. That's an open problem. I've thought about this. How quickly should you recompile? How much should you trust your compiled code? Because error characteristics change very frequently. Sometimes they can actually may not be possible. You may not be able to detect them as well. You just don't know because device provider has not given you up-to-date information. So best thing is to sort of run, as soon as you get your compiled code, you run it upfront. And that way you minimize your chance of being vulnerable to drift, because most of these errors drift a lot. And sometimes calibrations are localized where maybe portion of the chip you are using is not calibrated right now, but maybe the characteristics have changed. And that's why if you look at a couple of new efforts from IBM, for instance, they have this thing called Qiskit runtime. And the idea is you reserve your device and do things. I think that's the same reason why you don't want to probably put your job in the queue for a long time and you reserve a slot on Rigetti machines on AWS, for instance.
Can you predict how the error characteristics will change over time from how they've been changing based on a window of time?
It's hard because you may not have full understanding of all the data. Many of the times it's all proprietary data, right?
No, but the provider, can they analyze how the errors have been progressing? Then
it's hard because it's just hard to understand when your device will drift, right? It's like no matter how much I train a model, I can't tell exactly. With high probability, I can tell something, but if I'm dealing with a random process like noise, I just don't know how to tell. Yes.
So did I understand correctly from your previous answer that so calibration is not really a device level thing, but it goes into compilation output.
So yes and no.
Or rather, why do you based on your error?
So calibration is the process where you tune the device parameters. In that process, what you get is also how erroneous all those operations are. If you feed in that information to your compiler, you can develop better compilers. For example, think about JigSaw. If I use the calibration data, I know which qubits are most likely to fail when you do a measurement versus which are the best qubits to measure on. I can use that data to recompile my program. So yeah. But then again, there are some techniques where you might want to do some level of fine-grained calibration for exactly for your program on the fly. And for example, the work on ADAPT, which deals with idle errors, that essentially deals with that. More questions?
Are there devices where this is not a problem?
Ion
Like
trap.
this when you-
So yes, so trapped ions are much better in terms of this because you're dealing with atoms. They are fundamentally more stable than superconducting devices. But I don't want to again get in trouble. But there are other problems with trapped ions. You don't know how to scale them very easily. You're dealing with lasers and things like that. It's harder to scale. Any more questions? Do we study error correction today or no? Just kidding. Yeah. Okay. So that's a bit about NISK era. I was supposed to spend 20 minutes on it, but I'm very glad there were so many questions. You know, it's interesting because a lot of the times people don't tell you they are not following because they are like, it's quantum. Maybe I'm the one who is not following. So I'm very happy you all asked a lot of questions. So let's move on a little into what can we do as architecture people to understand quantum error correction in the near term. As I mentioned earlier, right, this is a very exciting phase and people are actually demonstrating quantum error correction codes because remember the fundamental goal of the quantum community is to sort of aid those fault tolerant operations. When you read a blog, it's all about breaking those RSA keys, right? And that's the final goal of the community. You want to build fault tolerant systems. And a lot of quantum error correction has been predominantly very, very theory related. And now with the devices space evolving, you're getting better devices, you're able to sort of reach a phase where you run quantum error correction codes and understand how they behave. So what are the challenges in quantum error correction that we as architects can contribute to? But even before that, let's try to understand a little bit about quantum error correction. First of all, it's significantly more challenging than classical techniques. Think about it this way, right? If you want to protect one bit of information, what's the simplest thing that you can do? Couldn't follow? Update it time to time. So something, let's say in the lines of triple modular redundancy, right? You take your data, let's say one bit of information, you replicate it, you copy it 3 times, store it, you periodically measure them and check if there was an error. If there was an error, do a majority vote, you can figure out what the error was. If you want more redundancy or more fault tolerance, you basically increase the redundancy. Let's say you do 5 MR, 7 MR. What's the fundamental idea that you're using here? You're copying the information, you're creating backup copies, you're looking and checking by measuring them again and again. Those 2 assumptions fail in quantum setting because you can't copy information. You can't copy a qubit into another. There's a fundamental limitation. And secondly, if you measure a qubit, it loses its state. So you can't really measure the qubits. So quantum error correction becomes a slightly bit challenging because of these fundamental limitations. And therefore, what in quantum error correction happens is that you prepare a logical qubit wherein you basically distribute your quantum information across several data qubits.
What should we mean by those? What's the big difference between the physical one, the virtual one? Two story in a normal computer or something? Like the virtual.
You take a patch of, let's say, 100 physical qubits, you do something there that gives you a logical qubit. So this one logical qubit is effectively supposed to have lower error rates than the 100, each individual qubits from those 100 physical qubits.
What's the technology that's used to store the virtual one? The normal computer?
No. It's fundamentally the 100 qubits as a logical qubit. It's like, think about TMR, right? The triple modular redundancy. If you want to understand what's the bit value, you read all three of them. So here, your logical qubit is essentially you encode it using several physical qubits, and you're using that redundancy in some sort of encoding and decoding such that you figure out errors in a way that your logical qubit has lower effective error rate. Is that clear, or there's a disconnect here? Okay. So you distribute your quantum information on those data qubits. You operate on them, but you don't measure them. What you do is, in addition to that, you use these parity qubits. These parity qubits, what you do is effectively it computes some parity information from the adjacent data qubits and then tries to give you the parity information. And once you have identified the parity information, you can use that to understand errors, or if you can track errors, basically. So think about it this way. If you're running an application in a fault-tolerant manner, you initialize your logical qubit. So you prepare those lattices. Then you do those parity checks. This is called syndrome extraction. The parity information or the bit string with zeros and ones is called syndrome. And sometimes the syndrome extraction is also called a stabilizer measurement. Those measurements that you do is basically you are measuring the stabilizers. There's a fundamental way you generate those parities. And then each time you do a syndrome extraction, you get this bunch of zeros and ones, which is your parity information. Now you use the parity information to identify where did the error happen. And to do that, you use a decoder. The job of a decoder is to find out if there was an error. In the event of an error, where did it occur? And what was the type of the error? Because remember, qubits, if you recollect that sphere notation, qubits are not just associated with a bit kind of information. It also has a state information or a phase information. So qubits can encounter both bit flips or phase flip types of errors. There's a phase associated. So you want to identify what was the type of the error, whether it was bit flip or phase flip or both. And if you do this repeatedly, once you have checked your parities, if you have identified your errors on those physical qubits, you can go fix it. And that's what effectively leads to you building this logical qubit with much lower error rate. And then only at the end of your application is when you measure your data qubits, they collapse, you retrieve the final outcome. And you run this as long, and you do this whole error correction as long as your application is run. And this way you can basically track errors periodically and sort of basically protect your quantum information. I'm ready for any questions.
Yes, please.
With the camera, I'll try to fix it. The camera's frozen.
Oh, okay.
Go ahead, Joel.
Okay. So, I mean, the rest of the slide makes sense, but I was mentally a bit stuck on that collapsal measurement. I understood no cloning. I wasn't sure if I understand that. For example, you showed earlier the C0 gate, and that looks almost like you're copying.
You're not copying, you're entangling them.
Seems similar. How are they different?
You can't copy the state of one qubit into another. If you have a qubit that's, let's say, 20% of the time 0, 80% of the time 1, it's in a superposition. You don't know what will be the state when you measure it. So you can't fundamentally copy it to another qubit. Because let's say like it's 20% 0, 80% 1, but it might collapse to 0 when you collapse this to 1. There's a fundamental limitation. Because it's
Okay, then so I'm still hanging that concept. Then what's functionally the difference from you're saying I'm not really copying because I'm not measuring, and then I feel like if I have one qubit and then I'm I guess entangling its state to a second qubit such that second qubit state is exactly, so when they're entangled in this way they are going
So
to
when you
overlap.
entangle, they are entangled in the sense that if you apply your gate on one of the qubits, because they are entangled, the other qubit will also change its states in that way.
So in this case, the data qubits, are they entangled or they are entangled with each other to have the same, let's say,
Yes, and you,
replication of the-
yeah. And then you sort of tie them to each other, you encode them in that way. And you basically, it's more complicated, but effectively you operate on them as well, because you just don't want to create this code, right? You also want to do some operations. More questions? Yeah.
So my question is coming from the theoretical side of how many data qubits we need to for representing a logical group. I guess this ratio depends on how accurately we want to represent, or how strong the error correction is.
Very good question. It's a game of probabilities. The fundamental idea about quantum error correction is that if you increase your redundancy, your logical error rate will exponentially decrease. How much you want? That depends on your application. Let's say your application can tolerate, let's say 10 to the power minus 6 error rate. Your physical devices are giving you 10 to the power minus 3. You calculate the redundancy based on this gap. If your application is basically able to tolerate only 10 to the power minus 12 versus physical devices giving you 10 to the power minus 3, the redundancy that you need is much higher. So this redundancy is what determines how you will distribute them in the form of data and parity qubits. So for example, if you take a distance 3 code versus distance 11 code, their redundancies will differ. And based on that, you will have the number of data and parity qubits.
But will it also depend on, let's say, so let's say if my program requires a 10 to the power minus 12, and the hardware is supporting 10 to the power minus 3, I need a 9 orders of magnitude
Improvement from that.
the logical to the
Yes. So you opt for a redundancy that helps you get that. Yeah.
But at some point I need to read all these data qubits also. So and I'm reading, let's say if I can only read let's say 2 at a time. So like the question that he
100 qubits at a time, let's
exactly.
say.
So
Yeah.
if I can read 100 qubits at a time, so that means reading 10 to the power 9 qubits is going to take so much time that the last batch would be changed by then. So that should also come into.
So it's an open device problem. So that's why you want a lot of parallel measurements happening at scale. And each company is trying to invest, I think, in both baskets, how to do things. Yeah.
When you said, so okay, your device might give you 10 to minus 3 array, and you might desire 10 to minus 12. What order of magnitude of redundancy are we talking about that you need? Is it like what you showed, like thousands, or is it like
Thousands?
Okay.
But again, it depends on your code. I'm talking about mostly surface codes. Again, as I mentioned, every stack in quantum is an open problem and people are working on it. So people are looking at low cost, low overhead codes. Like there was a demonstration of, not demonstration, I would say, but there was a quantum LDPC codes. One of my collaborators is working on it a lot. There's Flocket codes, honeycomb codes from Google, and they're effectively looking at that. More or less, I'll talk about it later in the next slide. Most people still now are focused on surface codes because it needs grid connectivity, which is very easy to build. Not very easy to build, but relatively easier to build compared to, let's say, all-to-all connectivity. So that's one of the aspects. Trap time systems, typically, they have demonstrated color codes. That's a style of coding. So think about it this way, right? You do different style of error corrections, like Huffman code, Hamming code, or this kind of different codings. You have similar notations here also.
Fundamentally, the problem is something like medical physics or something.
Device guys will kill me if I tell that. Yes, but you know, you want, again, definitely, if your devices are much better, you can actually reduce the redundancy a lot. And that's why there is this whole push. If you talk to error correction theory people, they'll be like, we need better devices to do error correction, right? And that's a fundamental idea why people are still trying to sort of reduce the error rates so much. Bridging from 10 to the power minus 4 to 10 to the power minus 12 versus bridging from, let's say, 10 to the power minus 6 to 10 to the power minus 12. The redundancies are largely different. You will be saving few thousands of physical qubits. That was a whole push for topological qubits from Microsoft, because those qubits are substantially better quality, hopefully, when they build it. But the idea was that then if your devices are so good, then you need to build smaller systems comparatively with respect to, let's say, superconducting ones.
Well, we can say like quantum computing is like is a problem, like it's partially for people from computer science and like a small percentage. The big issue will probably is more competition not going to work there. Do you say that?
I don't want to lose my job. No, but fundamentally there are issues in building large-scale quantum computers where you maintain very good error rates. That's a fundamental challenge. I can talk about this offline. Let's say some device people at a company X, Y, or Z, wherever I have interned, have told me that, you know, we can build these systems at a much larger scale. It's just that we cannot get very good error rates very quickly. So that's what is challenging. Going from 100 qubit system to 1,000 qubit system while maintaining the same error rates is a very hard problem.
If we maintain, for example, we talk about quantum computing in a way that certain kind of applications we cannot compute them because of the errors, right? The devices are very error prone, and the cost of trying to detect the errors doesn't scale well. So, but the problem is, if we is there anything we can do to tolerate, for example, some systems so they can still detect the errors very well and still be able to execute the rest of the applications that we have, or they are more exclusive completely.
I am not sure if I followed your question.
So my question is, can we have, like, what can we have a quantum computing, for example, that is able to detect, right, the errors so that we can compute more applications?
So you can detect errors. The challenge is then you need to do error correction.
Yes, but is there any way to tolerate the error correction? For example, must we be able to execute the rest of the application? Or they are completely not exclusive? What we lost, right, if we tolerate, what's the sacrifice that we need to do to tolerate these errors in order to execute the rest of the application?
Right.
Or would you like to take this question offline with me if it requires?
Yep. Yeah, I'll be happy to chat later because I'm not following the question a bit. More questions. I was before I had. Okay. But I'm glad we did with basics of quantum error correction in 15 minutes. This is good. So as I mentioned earlier, right, we are in this phase where we are building the systems. People want to understand error correction codes. I briefly talked about it, that you want to demonstrate quantum error correction codes, and surface codes are probably like one of the widely recognized most promising error correction candidate today. The surface code logical qubit looks something like this. You have this logical qubit patch. The data qubits are the white qubits. And as I mentioned, you have those stabilizers or the parity qubits that you want to measure periodically. As you can see here, there are two color codes. And they are because you want to detect two different types of errors in quantum, bit flips or phase flips. So the X stabilizers and Z stabilizers are essentially designed to handle those two types of errors. Depending on the type of your error, your adjacent stabilizers will indicate an error. So for instance, if you have a bit flip, which is technically termed as an X error in a quantum computer, your adjacent Z stabilizer, which is the parity qubit A here, that will flip. So it's adjacent to that data qubit. Alternately, if you have a phase flip or a Z error on that same data qubit, it will cause the adjacent X stabilizer, or which is the qubit B shown here, to flip. If both errors happen, both A and B will flip. And what you're getting out of it is essentially, if let's say both A and B flip, your decoder's job is to figure out using that information, okay, there was an error on that data qubit that's here. Okay, so you sort of do that reverse engineering. Here is the code which is of distance 3, which means it can correct up to 1 bit of error or error chains of length 1. As I mentioned earlier, if you want to have more fault protection, you basically want to have high redundancy, which is again, you want to increase the distance. So if you want to run something like Shor's algorithm or Grover search algorithm that I mentioned earlier, you need a larger distance. Okay. And the surface codes I again mentioned earlier, it's widely regarded as a very promising error correction candidate. And as you can see here, it needs a grid kind of structure, which is easier relatively to build. And one of the key things, and people have, this work was done last summer, right? And since then, there has been already a couple of demonstrations of error correction codes, other types, color codes, repetition codes. In fact, a color code demonstration came out when we were working on this project. So demonstration of surface codes and other types of error correction codes represents a very significant milestone in quantum error correction, because that gives us intuition and understanding of how to build those large systems in future. So now the problem that I want to describe is about real-time accurate decoding. A lot of key terms. Decoding is basically identifying errors. If you remember, I told you, you get this parity bit string. You have to take that information, digest it, and figure out where did that error happen, what was its type. That is what decoding is about. And if you can't decode accurately, you will assign errors somewhere else. For instance, if you look back in this slide, let's say your error happened here, your bits flipped here, but if your decoder is inaccurate and assigns an error to this qubit, you are introducing an error yourself to the system, right? So your decoders have to be very accurate. And then you must be doing it in a real time. As soon as errors happen, you fix it before they accumulate, right? Let's say you have a, back to the classical understanding, right? Let's say you have a triple modular redundancy. If you've detected one bit flip, you want to go and correct it, because so that next time a bit flip occurs, you don't want to mess up so that it becomes uncorrectable. So this is a requirement from quantum error correction, that you want to be able to decode or identify errors very quickly, very accurately. Now, how quickly, right? Typically, if you look at most current systems, we are talking about a cycle time or a quantum error correction cycle of about a microsecond. And in future, we expect this to reduce. Why 1 microsecond? Because that's the time it takes you to generate a syndrome. And you want to correct as quickly as you get a syndrome before your next syndrome arrives.
So I think I'm missing how this looks in a system. So you measuring, I guess, your qubits, and based on your measured values, you're decoding.
Yes.
And then then I guess you're somehow restarting you're feeding these values back into your
Control unit, right? Yes.
Okay. I'm not sure I understand why this needs to be real time.
If you don't correct your, sorry?
Why does it necessarily need to happen within 1 microsecond?
because you want to correct as frequently as you can, right? Else your errors will accumulate. If your qubits can only, let's say, hold on data for 100 microsecond or 50 microseconds, think about the exponential decay. There's a
But I think that's again what my question relates to. I don't get why, so since we already measured anyway, why are we still worried about qubits holding our data?
because you need to correct and do this process again. You do this repeatedly. If you
So we keep some state in qubits still? measure only
Yes.
our Qubits?
Yes, so you only measure your parity qubits
Okay.
and you do this repeatedly. So that's what lets you protect your information.
So what is the runtime requirement for different devices, let's say, at what order, and in terms of, let's say, seconds, it should be?
So yes, for superconducting devices, like the surface code study we did, we looked at the syndrome extraction time. That's the fastest you can get your syndrome. So you want to correct it as soon as you can get your next syndrome, because else you will have uncorrectable faults. So that's about 1 microsecond. There are future predictions. For example, the next work I'll talk about, there are predictions that you want to do this at a much faster rate, something about, let's say, 400 nanoseconds. It depends on the technology as well. For example, if you look at trapped ion systems, you have slightly more room in terms of how fast you need to decode. So in that case, maybe you have a few seconds or milliseconds. So the timing requirements obviously change based on your system or the device technology. It also depends on your decoding algorithm that you use. And there are specifics to those kind of things.
Yes, one question. When is the quantum, this evaluation is done at software or hardware level?
Very good question. I'll talk about it. Let's go. Sorry. Yeah. So, and back to your question, I will come to yours. It is easier to do with the slides. But back to your question, this 1 microsecond, why is this so tight? Remember, you have this user who is sitting, let's say, maybe at a room temperature, hopefully, or somewhere on the other side of the earth, right? And then, so effectively, you send your instructions, right? And so you use this control logic to control your qubits. You send your error correction instructions. You read back the qubits at the readout or measurement logic. You read the syndrome. And this is where the problem occurs. If you look at most theory works in quantum error correction, they actually, what they do is they take this and then send it to the software. So they send it outside the fridge and they consult a general purpose machine, run the software algorithm. This is very hard to do in a typical setup because your qubits are at a few millikelvins. Your control logic, I'm not going to talk into specifics, but maybe inside the fridge, maybe outside the fridge. Then you get all that data at your readout logic. You send it to a general purpose machine. This is all very hard to do in a 1 microsecond, I think you will all agree. And previously, everyone was using software until I went to an internship in summer of 2019 at Microsoft. And that's a work I'll talk about a little later, but effectively, these were all very slow because you can't decode in time. And so this is a big problem in real-time decoding because you want to identify errors and prevent accumulation of errors by doing error correction online or in real time. And software was just very slow. What happened is most of these error correction or decoding specifically works were very focused on theory heavy or very theoretical. They were using software implementations. And we changed that basically. So this was a work that was actually done at Google last summer. And we came up with this whole framework or design called LILLIPUT. And the idea of LILLIPUT was to do this real-time error correction, but for small surface codes. How can you do it faster? And that was the whole agenda for this project. And then when I started the internship, this was my goal. And I said that, okay, for this kind of work, you don't really need to use software decoder. How about just lookup from tables? Remember, what your decoder is trying to do is take those parity information and understand which error happened on which data qubit and so on. So you're trying to assign errors to those data qubits. You can store those assignments in a lookup table and then look it up from there in real time, which is exactly what we did. And then what the lookup table is indexed with is basically the syndrome, and the entry in the table gives you the error information. The advantage of this kind of design is it's low cost, it's low latency, it's very accurate because you can program it with the best known decoding algorithm that you have. And then very interesting is that it can be fit onto FPGAs. Why is that interesting? Because if you look at most existing systems, they actually use control and readout logic built in FPGAs. And so this can be seamlessly integrated in the system. And that's what makes LILLIPUT a very attractive solution for practical adoption. In fact, when I started my internship, the whole agenda was to kind of come up with a solution that solves real-time decoding in small surface codes, but it's easier to sort of build that design. I was kind of told, don't go down the silicon ASIC route.
This makes sense when we have yes, few parity bits, but you showed that one would want more parity bits if the application is very innocent.
I'm going in that direction.
Okay.
So Poulami, where is the FPGA located physically?
I cannot talk about it.
I see. So, but in general, would its activity or like power consumption affect the errors that you observe, and then do you calibrate for that?
If you put it inside the fridge, it introduces additional noise channels to your qubits. If you put it outside the fridge, there are other challenges, having bandwidth issues,
Yeah, because
talking to the. Yes, challenges I cannot talk about.
So this is very proprietary information in which temperature domain.
Yes, yes, yes.
Can you do it without software, without alignment software, like the recording phase? Can you do it without alignment software, just on the quantum computer?
How would you do it? No, because you need to use the classical algorithm to understand what error happened, right? So classical algorithm can be either software or hardware. Yeah.
So there is no quantum.
We better not get into that. Recently, I'm working on a project where I'm using machine learning to design quantum machine learning circuits.
So Poulami, how is so imagine a scenario in which for some reason the FPGA is inside and like you can handle the cooling. How would the FPGA operate reliably based on the temperature, like different components of it? Would they be affected by it?
So I think there was some open study by a group at TU Delft or somewhere. I am probably messing up the source, but probably TU Delft folks, where they showed that they can actually run FPGAs at 77 Kelvin. There was a work from Swamit, who was at Microsoft in a summer, and they studied, you can put DRAM inside a fridge at 77 Kelvin, it works. Cryo DRAM works. There were several follow-ups. The FPGA one, I'm probably incorrect about the source, but they have shown it to work. So, yeah.
Okay, thanks.
Why can't we use or techniques?
If you want to use, so quantum LDPC codes were pretty much dormant for a long time until few months or maybe a year ago. The challenge is it needs a different kind of connectivity, which may be hard to build. It needs a lot of long range connections for that kind of codes to work. So it's not just a simple grid connectivity that I showed you earlier. But there is a lot of growing interest in quantum LDPC codes. I'm myself very interested, may or may not be actively working on it. But effectively, I think there is a lot of interest in that because of the reduction in the redundancy, for sure. And if you are interested in it, I highly encourage you to read one of my collaborators' works, Nicola. He's kind of working on it for a couple of months now.
What is LDCP or quantum LDCP?
So you need fewer redundancy, like lower redundancy, so fewer parity qubits, and encoding is kind of smaller. So the redundancy you need is lower than surface codes. But the structure of encoding and the connections you need to encode the operations and how you encode the information is different. There's also a big catch over there. These are getting developed. So how you decode kind of stuff for those kind of codes is an open problem. For surface codes, there's a gold standard. You do minimum weight perfect matching decoding, it works. It's like the IUPAC standard. But for color codes or LIPC codes, these are still open. You had a question.
So one of my questions is, without this problem that we have, including 10%, and do you think it would take a long time to enable, for example, quantum computer for normal users? Like having a computer itself?
So I think there will be there are already applications where a lot of normal users, in the sense, some stuff like automobile applications, or there was something from finance, those kind of optimization problems, people were looking at it, and that's something in the NISK era that you want to have. And then other applications like different chemistry applications and stuff like that, you probably need to wait a few more years. I was recently at the Heidelberg Laureate Forum, and there was this post-quantum cryptography session, and Adi Shamir said he's very confident that things will be better 10 years from now.
Because I have some people saying that you don't even know how to manage it.
So quantum is a field where you will deal with a lot of enthusiasts and a lot of skeptics. That's how it is. But I think, I mean, I am personally from a traditional architecture background. I'm working in it for quite some time now. It's very exciting. There are a lot of open challenges, and the field is headed in a very good direction. There's like if you think about it, right? Like when I started my PhD, I was using 5-qubit machines. Now I can access 127-qubit machines. They are better. The size of the quantum programs that I can run more reliably grew up from 3 qubits to 15 qubits. So that's good progress. And I think this is all headed in the right direction. There were a lot of demonstrations from quantum error correction perspective. Google demonstrated surface codes. Honeywell actually demonstrated color codes using a very, very similar idea. In fact, they put their paper online on arXiv when I was writing mine, and it was under review at Google. And I was very stressed because reviewer may complain that, this is not novel enough. There was a demonstration of repetition codes. So there is obviously a lot of things happening. So I hope it remains an exciting time. More questions before? Oh, okay. Quick recap. Error decoding is effectively about taking your syndromes and trying to detect errors in the first place, if an error happened in this cycle or not. That's the first thing you need to do. Then use that information to understand what was the error, right? So to do this detection, what LILLIPUT does is essentially it uses XOR between syndromes from consecutive rounds. And sorry. No, I'm good. Thank you. So let's take an example of why that works, right? So think about it this way. Let's take this logical qubit that I was demonstrating so far. Let's say in the first cycle, you don't have an error. And for simplicity, let's only consider the X stabilizers or those red patches. What happens if you measure those stabilizers? No error, you get all zeros because all parity checks are successful. In the next cycle, let's say you have a Z error on this qubit A. Well, the adjacent stabilizers flip and you get a 0, 1, 1, 0. Your qubit state has basically changed internally. In the cycle 3, you don't have an error, you reread the same parity, right? And in the next cycle, let's say you have a Z error on this bit on this qubit B, now its adjacent stabilizers will flip, which means this will flip, and it was previously 1. So it will now flip to 0. This was 0, it will flip to 1. This will remain a 1, and this will remain a 0. Let's see what happens. Yes, 1, 0, 1, 0. From the decoder perspective, this is all the data that you're getting from the qubit substrate, and you have to go figure out what error happened. So to first of all detect if an error was there or not, you keep a track of prior measurements in a FIFO and then do XOR operations. And as you can see here, you have successfully identified how the errors are in each of those cycles, right? And so in hardware, you basically use FIFOs and XORs. Then the next step.
Sorry, but I didn't follow, like, sure, I can access and I can convert back, but why? Like, why would I want to use XORs?
Why would you not want to use XORs?
I don't know, before we weren't using XORs, so I.
No, because so what happens is you need to detect changes from the previous round, right? You don't want to double correct, right? So that's the thing. Here, for instance, if you use this as your syndrome or input to your decoder, you use this as your input to your decoder, it will give you a correction, but you have previously corrected already in this cycle, right? So you don't want to do the correction again and again. And that's why you need to know if error happened exactly in a specific cycle or not. That's the first thing. In the next case, if there was an error, what was the change from the previous cycle? You need to detect that, because you think of it this way, right? You have 1 cycle, you have 2 cycle, you have 3rd cycle. You need to understand specifically what order things are happening, right? Clear, or was I very defensive?
When is the correction of this?
Very good question. I was hoping no one asked that. No, it's a bit tricky. Essentially, you can hold off until your correction until a certain point, but after some, if you want to do a non-Clifford operation, you have to correct before that. So then you need to do a feedback. So what you do is you maintain an error log, and then the moment next instruction is a non-Clifford, you go and correct it. So you don't correct again and again, but you do this. Challenge is every 5th operation is a non-Clifford. It's like every 4th instruction or 5th instruction is a branch, that kind of stuff. So every 5th operation tends to be non-Clifford on an average based on some profiling of applications. So yeah, so that's when you want to correct. So that's why you design your decoders to handle that latency. You want to be able to correct all the time. Otherwise, you keep a track of the error logs and you hold on. So let's say your error X happened in cycle 1, 2, nothing happened. X error happened on the same qubit in cycle 3, so they cancel each other. So you don't apply correction and so on. But let's say in the 2nd cycle, you had to do a non-Clifford gate. In that case, you will apply that correction. Okay. Okay, moving on. Okay, this is a slide I don't know. I'll see how many questions I have. So think about it this way, right? I did talk briefly about different types of errors in the beginning of the presentation. And your decoder must be able to handle those different kinds of errors. What this means is that it's not only the errors that accumulate on your data qubits, but think about it this way. When you're extracting the syndromes, you're doing some parity checks. You're trying to do some operations, and those gate operations can fail. So you need to be able to tolerate them. When you're doing parity qubit measurements in every quantum error correction cycle, those readout operations or measurement operations can fail too. And finally, at the end of your application, you are measuring those data qubits, which is this logical measurement. Even those can fail, right? So these are the different types of errors that your decoder needs to deal with. And how does it deal with it? So first, let's think about errors on data qubits, right? Remember, when I was talking about the surface code lattice, you observed that if there is an error event on a data qubit, it leads to parity events on the same cycle in space. So they lead to what in error correction terminology, people call it a space-like event. And the conventional notation of representing all of this is a decoding graph that you see here. And these red bits or in this graph, the nodes are used for parity qubits and the edges denote your data qubits. And what your decoder tries to do is take those non-zero parity qubits and tries to match them such that you assign errors to the data qubits. Okay. And sometimes you want to match, sometimes let's say this whole error is on an event on this boundary of the graph, which is called the code boundary. In that case, it's most likely one of these kinds of events. So you assign an error to the boundary and so on. But the key idea is that you match those events such that you're trying to neutralize the effect. So for example, in this case, if you match these two parity bits, your decoder will assign an error to the data qubit that connects the two, and so on. That's what your decoder is trying to do. If you look at gate errors during syndrome extraction, how do they manifest? So if you look more into theory, but effectively what happens is that they come up as space-time events, like you see here. Okay, so you have them spread out in the form of a diagonal. Okay. Measurement errors or readout errors on parity qubits effectively come up as time-like events. So the detection event will look something like this. These are the signature of the detection events that you will see. If you want to decode them effectively, you must be able to decode multiple rounds of syndromes together. The final kind of error, the readout error on data qubits, by that time, effectively, when you measure your data qubits, your error correction cycles have ended, so you don't have anything to do there. So you measure your data qubits and then try to sort of recreate a syndrome from that logical measurement, and then compare it with your last error correction cycle round to see if an error has occurred or not and correct it. But what all of this effectively implies is that LILLIPUT can handle errors in any operation in the quantum hardware. And that's what you ideally want. Any questions? So that's the type of the errors that you deal with in LILLIPUT. What you do is you have these lookup tables, right? So you need to fill up those lookup tables. And to do that, you basically program the lookup tables using the minimum weight perfect matching decoder, which is ideally considered as like the gold standard for decoding surface codes. And what you do is you prepare this lookup table data offline. You load your tables before you start off your experiments, and then you basically can decode online. To prepare the lookup table data, you basically go through all the error events and then fill up the table. And this way, LILLIPUT effectively uses this offline data that it prepares to decode online. Fair enough? To give you a flavor of how this thing operates in a realistic setting where you have multiple cycles, you effectively take this current window or multiple rounds form of thing, and you go on as the error correction cycles proceed. The top cycle is the oldest round and the bottommost is the newest round. And this helps you, the streaming mode helps you basically to account for events that will cross the boundary. So you're looking at a window, right? Then the next thing is, how do you assign errors? Let's say you have this kind of window. The objective of LILLIPUT is to take in the errors in all of this, all the error events within the window, and then assign errors to the oldest round. Why it waits and assigns errors only to the oldest round? Because, well, let's say you have this time-like error here. If it proceeds forward, time-like error, basically this round is not yet visible to you, right? So that becomes a problem. If you want to assign errors right away, you will assign it here and then it will be premature. So you wait for the next round. And then you assign errors to the oldest round, and then you also keep a state of what keep a track of the state of what you have assigned previously. For example, let's say you have this kind of event. You assigned errors, you matched this event, and then you move on. But if that previous matching information is not available to you, what happens is you again might match it incorrectly, right? because this event was actually matched already. So you need to have that information. So you track some sort of state information in the lookup table entries themselves. And overall, you do this tracking and error logs to sort of keep a check on the errors. This is an overview of what the design looks like. Not going into details, but just an end-to-end system picture. One of the main challenges of LILLIPUT is effectively going back to the question he asked, is that your memory will depend on the number of parity bits, right? And that's correct. Let's say I want to design the tables for the lookup tables for LILLIPUT that, let's say, decodes a surface code of distance 3. Let's just say we decode using 1 round of syndrome. What happens is, you have 4 bits of syndrome of each type, the blue or the red. So your lookup table essentially is indexed by a 4-bit address. And each entry in the table is trying to assign errors to one of those 9 data qubits, which means the entry comprises of 9 bits for error assignments, and then 4 bits to store the state information that I talked about that you need to handle the operations. So your table is pretty much like 2^4 entries and 13 bits per entry. Okay. Let's say you want to design the same decoder, but you want to handle different types of errors, and you want to build the decoder using 2 rounds of syndromes. Well, you now have 4 additional bits of syndromes coming in. So now your table size, each of them, increased from 2 to the power of 8 to 13 bits. And this becomes challenging because, by the way, this is a common notation. D equals 3, M equals 1 means you're decoding for a distance 3 code using 1 round of syndrome. M equals to 2 means you're using 2 rounds. So now if you increase the distance and you compute the sizes, it basically it increases very rapidly, right? And this becomes a very big problem. Let's say even like 148 megabytes is hard to handle on the on-chip memory of the shelf FPGAs, right? I think the maximum you will get is just a few megabytes. So we had this problem when we were designing this. So we tried to come up with a solution. And then one of the things we realized is that, well, if we look more carefully into one of the access patterns for these decoders, the figure here shows a probability that the different memory addresses are accessed based on their Hamming weights. And this corresponds to a distance 3 decoder. If you see more carefully, because not all error events are equally likely, very large Hamming weights are very, very less frequently accessed. Moreover, in many cases, if you look at the Hamming weight memory addresses with moderate Hamming weights, you will see that even if you access them, it doesn't matter. They anyway still lead to uncorrectable faults. So our solution was that why even store them? So instead of storing all 2^n possible entries for a table, just store selective entries. The next part of it is this. Look more carefully into this surface code lattice. Each cycle, what you're trying to do is assign errors to one of those 9 data qubits, these ones. But remember, this is a code of distance 3. It can only correct up to 1 bit of error, which means you won't be assigning too many errors, right? And what this means is that the data themselves inside the lookup table entries are quite sparse. And so why not compress them? So that's how we proposed compressed lookup tables, and we tried to reduce the memory complexity. And if you look at the performance, the figure here shows the logical error rate and the decoder failure probability, but it doesn't matter because your decoder, the probability that you encounter a logical failure by that time, if you carefully design the lookup tables, once you compress them, it will not hurt your performance. And here, as you can see, is the logical error rate for physical error rates. And for instance, if you have a physical error rate of 10 to the power minus 3, there is an exponential suppression in the errors for distance 3. So this means that this whole design is working. And this was very impressive. So the compressed lookup tables have negligible impact on accuracy, your logical error rate is lower than your physical error rate. And then all of this, we were able to actually decode within 42 nanoseconds of latency. It required less than 7% of logical utilization on most FPGAs. It was sufficient for distance up to distance 5, which is fine. And we got about 107x reduction with compressed lookup tables. And this, all of this package together, you see, it gives us a very low cost and accurate solution that can be adopted more practically in the near-term systems. And before I head on to the next phase of my talk, I'm looking for questions. Is everyone sleeping?
This memory bound workload.
Actually, not the.
I mean, we're talking about investing that from.
So-
I mean,
The part that we implement the mitigation.
yeah, the compression is definitely has some very footprint.
So your tables become very large, right? That's what he was also raising a question. If you have to build a 148 megabyte table on the FPGA SRAM, you just don't have the capacity. So that becomes a problem.
Yeah, so I'm thinking about maybe a memory solution to help them.
No, but it's a PGM in to where.
I think that's a-
not even backed by something else.
Ask what they want you to do.
Because it already has FPGAs in the.
But the logic is already.
Yeah, the control logic is already there.
Control, readout logic,
Yeah.
everything. So you get your syndromes and the readout logic, it's already there, just integrate it over there.
So it makes sense for them to have the correction logic also in the same substrate that the control logic is. But then the problem is that the correction logic.
Can I have some water?
Uncompressed.
Thank you.
I mean, you don't need computation, it's just a lookup technique, that's it. I mean, yeah.
So at some point, yeah,
No, nothing.
at some point, my advisor wanted to name this paper KDIT. Can't decode, doesn't even try. And I'm like, that might go either way, so let's not name it that way. But yes, it's basically like just look up, don't do any computations.
So what, did you give any number on what the actual size was in the end of the lookup table? Or can you give a number?
It came down to a few kilobytes, and for the largest size, it was I think about 1 point some megabytes. Don't remember off the hook, but it's on the paper actually. We were able to fit it on.
So I was wondering also, I mean, it makes sense, and I guess it's different to kilobyte than hook. Is there obviously a reason that these this decoder cannot be encoded kind of in combination with logic in the FPGA? Like, is it because the offline steps that are?
You can develop combination logic, which I will talk about. Like basically you are saying like a very application specific implementation for that algorithm, right? To the best of, I think, my knowledge, minimum weight perfect matching is a very beastie algorithm that is very hard to implement. The owner of the algorithm himself, Austin Fowler, at some point wrote a paper that you might need multiple ASICs together to decode this, and for obviously a bit larger code, and then talk to each other to do this all just for a single logical qubit. So for the first internship I did at Microsoft, I mean, my second internship at Microsoft, but the first one in which I looked at error correction, that was in 2019, is the next work I'll talk about, which does that, a silicon ASIC. But then what happens is you sort of, I won't say can't do, but at least we did not look at minimum weight perfect matching for that kind of stuff, because we were looking at slightly more future systems where the error rates are lower and you can use a more approximate algorithm than minimum weight perfect matching. For the near-term error correction studies, given the error rates and the fact that you are still doing things relatively on very noisy systems, you wanted to build the most accurate decoder you can. In fact, if you look at a recent surface code work from Google, they used multiple decoders depending on the errors. So it's kind of dicey in that sense. It was a 7-stage pipeline. Depending on the frequency we could clock it, we decided a frequency. It was a fully pipeline design, and the 42 nanosecond was the maximum that we could clock it at, but somewhere really faster than that. FPGA. Yeah. Does it answer your question? So actually, I think I have a backup slide. I can talk about it later, but basically, depending on the decoder configuration, the things change. The rest of the logic also needs to work, and that determines the frequency. So it's something around that. 42 was for distance 5. Yes, which is way faster than what I was asked to do.
Is the distance that the distance is what is increasing the lookup table size to be exponentially, right? So what dictates the distance? I guess the overlapping error is what one of the conditions.
No, what dictates the distance is basically you can build a larger code, you can correct more errors. So if you look at the logical error rate for distance 5 code that we studied, it was lower than what distance 3 gave us.
Okay, but let's say from practical perspective, like what stops us from, let's say, okay, at 5 also? I mean, is it that the
What stops it at 5?
yeah.
My internship ended.
From practical perspective,
No, but on a serious note, I think when I started my internship, my job was to build the decoder up to only distance 3. Just give us real-time decoder for distance 3. That will be good. And I was like, let's challenge ourselves and let's try doing up to distance 5 and so on. One of the other challenges is that it's not about just the code size, right? You want to be able to decode with more than one round of syndrome. That also leads to the complexity, right? So yes, and then the question follow-up would be what happens at distance 7, 9? That's the near-term things that you want to look at. I may or may not be actively working on that.
I'm just trying to understand, like,
Yeah.
what.
So it's like baby steps, right? I think first you start off by demonstrating just with a patch of, let's say, 50 qubits, and then you move on to the next distance, and then so on, right?
So, yeah, so if I put the question in a better perspective, let's say, what is the requirement? Is there any headroom for the requirement, or is like always the better is higher the better?
Higher the better in the sense more redundancy means more suppression of errors, and you want to even understand if you can really suppress that. I started off by saying when I discussed error correction, right, that a lot of it is in really theory. Most of the error correction talks, most of the error correction things that you will know about is in theory, and we are reaching that point where we are trying to understand how it really works at the system level. And now we are coming into these challenges that, decoder is not fast enough. So let's have someone from architecture background to do it for us. That kind of stuff.
What other tasks regarding, let's say, maintaining different aspects of reliability or performance in this quantum computing do you expect in the future might require hardware acceleration?
In terms of?
Basically, so now we talked about decoding, right? So, okay, there's a need for hardware acceleration. So are there like different aspects generally?
Yes, there was another paper from Swamit who was my senior in our lab, and he also had looked at some of the problems in this specific, not decoding as such, but controlling qubits at scale. That's an open problem because qubits are qubits, but you still need that classical architecture to sort of do the control operations for you, to send those instructions in synchronized fashion on time, get the data back, correct it, have the feedback, go do something else, that kind of stuff. And that layer is actually like a classical thing. And that's why if you look at when I talk to people, a lot of people just are like, oh, you work on quantum. And then I'm like, no, what I do is very different. It's just applying several software or architecture level knowledge to build quantum systems. And most of that system stuff is what is the missing piece in quantum. Yeah.
Maybe a bit of a curveball question. Is, I guess, a lot of focus here is on being low latency. And the main motivation is because qubits don't contain data for very long. Does the work become useless if in a few years somehow we manage to hold data much longer?
No, even then what will happen is there is always an exponential reduction, right? As your gates become better, for example, when you talk about slightly future systems, which I'll talk about next, you actually try to correct even faster. There are models that predicted that, we can reduce the syndrome generation time to up to 400 nanoseconds, which is what we use to study now what happens. And the key idea is this, right? The probability that you encounter an error at 400 nanoseconds versus 1 microsecond, they're different. And that's what is sort of driving this. You also want to correct very quickly, operate on them, right? You don't want to be doing this forever. And so if you can correct frequently, you are less prone to errors. So you have more computations that you can do. More questions? More questions? No? Okay, moving on. I talked about error correction quite a lot, but most of the focus so far was on the near term, right? And I think we discussed this a bit, that what happens when you have these large systems. And as I mentioned earlier, you want to be able to do this error correction even faster. And the hope is that you're dealing with systems where you're trying to decode larger distance codes for a large number of logical qubits at a time. And what does the system level challenges look like? And so the fundamental idea of being able to decode in real time holds true. You want to decode accurately, that holds true. But it's just that now you must be able to do this at a larger scale across larger distances for more qubits, because you're probably running an application that consumes 1,000 logical qubits and you're trying to encode them at distance 11 or 15 or 20, and then trying to run error correction on top of that. So what does the system level challenges look like in that case? Of course, software is very slow and you can't use it. LILLIPUT is accurate, fast, scalable for small distances, but when you look at larger distances, it's not very useful. And so this work was done summer of 2019 when I was at Microsoft, an intern. And what I looked at is that most of the decoder studies do not analyze the system level challenges involved in building decoders. When I talked to the error correction expert, in-house expert at Microsoft, and his opinion was that, yeah, you build a decoder, somehow accelerate it, and then put a decoder for each logical qubit. And then the question was that, okay, then what happens? Because you're probably running inside a fridge in most cases, and then you don't have that much of power budget. How are you doing all of this? Do you want to put your GPU inside? What's going on? That's when I actually started looking at this problem. And the key takeaway was that, you just don't focus on the latency or accuracy, but you also want to sort of have this notion where you're finding out ways to scale this at the system level, where you're dealing with many logical qubits. And so we started off with the union find decoding algorithm, and that is what translated into what I call the AFS decoder. Not very creative, it's accurate, fast, and scalable decoder. And I will briefly talk about the union find decoding algorithm, first of all, so that it helps you understand why we came up with this. So let's start off by using this example, and the papers were written at 2 different times, so the code coloration looks different. But here, basically, you have the stabilizers as the green and the yellow qubits, white ones are the data qubits. And for simplicity, let's understand using just the Z stabilizers, which maybe are the green stabilizers, right? And let's think about what happens if you have an error indicated by the Z stabilizers. how does this algorithm behave? So let's say there was an error in this qubit and these bits, these parity bits or these stabilizers flipped. Again, that's all the information the decoder sees. What the decoder does is that it grows clusters surrounding those non-zero parity bits until it is able to merge them into a cluster that has even parity. So in the next step, you clean up those edges and you merge them quickly. So this is the first step of cluster generation. When you have a larger decoding graph, for simplicity, I showed you just small one, right? But if you have a larger decoding graph, which is decoding using multiple rounds in a 3D graph, effectively, you will eventually end up generating multiple such clusters, right? In the next step, what you do is you traverse through the cluster. You go from one end to the other. And this step of cluster traversal or the graph traversal is what allows you to visit all the data qubits or edges in your decoding graph where you might be assigning errors. And then finally, obviously, this is a simplified graph. Your graph might actually diverge from here, which is why you traverse in one direction first, and then you roll back, kind of do this reverse traversal, which is also known as the peeling step. And this is what actually is when you assign errors. And so in the peeling process, you basically go back the reverse way, check the syndrome bits locally and do this error assignments. And this is how, for example, in this case, you had these two Z stabilizers indicating an error. In the end, you ended up assigning an X error to this data qubit, which is what would have caused these bits to fail in the first place. Clear? So we started off with this algorithm, and then the first thing I did is that how about leveraging microarchitectural optimizations to improve the decoding latency? And then we essentially came up with this 3-stage pipeline implementation. And then we take the syndrome, pass it through the graph generator, which creates these clusters. Once those are created, you do a depth first search, like graph traversal, which is the DFS engine. And then you go through the correction engine that does the peeling. But once you have designed this 3-stage pipeline design, what happens is that, well, now you can effectively parallelize operations. For example, when you are in the peeling step for one of the clusters, you can use the DFS engine to sort of traverse the next another cluster, and you do them sort of throughout the error correction cycle. And this gave us basically the AFS decoder, which effectively translates the key 3 steps of your union find decoding algorithm into 3 distinct pipeline stages and implements it. Okay.
So is the union finding decoding algorithm is a standard one, or is
Good question. So usually the gold standard is minimum weight perfect matching. This work focused more on slightly futuristic devices where the error rates are lower. And in that case, you use union find because effectively it kind of overlaps with minimum weight perfect matching. So it's still approximate. There is obviously some level of accuracy difference from minimum weight perfect matching, but it is still widely used because it's way more practical. You can't be spending like, I don't know, 50 microseconds trying to decode and then your errors have happened. So it's better so error correction is basically like that. It's a game of probabilities. Okay. And then this is what the whole design looked like. But what you can see here is that it included a lot of tables, stacks for the traversal of the clusters. And then you sort of have those registers, and then you hold syndrome locally in registers. And then here you have stacks. What this meant is that, well, again, we ended up with a memory intensive design. It had a lot of registers, tables, and stacks. Questions? Sorry?
We like memory.
Probably I was assigned the project because my advisor likes memory.
I was having the same issue. Yeah, on this side, we still have memory as a problem.
Yes. So we did some calculations, and it turns out that, let's say you have different logical qubits between 500, 1000, 2000. And based on the distance, you would need few megabytes or few gigabytes, right? And I mean, it's more like a futuristic design, obviously, but this is a problem. And why is this a problem? Because the technology for implementing decoders is still an open problem. People are exploring superconducting designs so that they can do fast decoding, they can do fast control, or they're also trying to understand CMOS designs. And each technology has its own problem. Superconducting devices, they are on a very, very tight memory budget. You don't have enough memory. I think the largest memory demonstrated so far is in the order of few kilobytes, right? So you can't build this design. The second challenge is with CMOS is that you're running on a very tight power budget. And this becomes very important for especially if you're running everything inside a fridge, because now if you, first of all, you have a budget, your fridge just specifies, I can only give you 1 watt, right? That's first problem. Second problem is that if you consume too much of power because you're running a very hardware inefficient design, then the problem is those, basically that heat that you dissipate introduces new error channels to the qubits because they are close by. So you want to ideally have very hardware efficient designs for this space. So that was what we had a problem with, that, you know, the memory requirement of AFS is not very, like, it scales very rapidly as you grow the system size. So how can we reduce it? Any questions? No, your light memory. So then, go ahead.
I just, if you go back to the previous slide, for depth 11 or let's say for depth 25 also, both of them scales much less as compared to LILLIPUT. Okay. The memory requirement itself.
Yes, because the designs are different. Here you are not using the, yes.
LILLIPUT, if we remember, like for depth 5, it was reaching 120 around.
148, yes,
Right?
yes, because you're storing all possible combinations. Yes, yes. Here you're decoding on the fly.
So, but there, I believe there are superconducting memories now that can give out the megabyte memory, right? I thought huh? No, not gigabytes, megabyte. That's like the bottom of the green.
It's still about a few hundreds of megabytes in this regime.
So, but the bottom of the green line, one could make kind of handle.
Yeah, so I mean, at least this was not the case when, first of all, we studied this. Also, even if you're building superconducting memories, as I mentioned, you still have a power limitation. You want to consume as less hardware as possible inside your fridge. So that problem still remains.
The power is also an issue for superconducting.
So if you have more memory, you will need more power to operate them. Yeah. All right. Good. Good to go. Okay. So I went to so the union find decoding algorithm was actually developed in Microsoft by one of my collaborators, and I went up to him and I said, well, what happens when you want to scale the systems, right? You are considering only 1 qubit, and his point was that we do this because we don't want to hurt the accuracy. You give each logical qubit its own decoder. That's what the assumption is. People have not studied multiple qubits. And so that was a fundamental inherent assumption among error correction folks, is that you give dedicated decoders, let them use all the hardware and or that time software, and they will figure it out. And so the key takeaway was that you want to, like, you're optimizing in this way where you are basically trying to have the best decoding capability, but that leads to this increasing hardware cost. And on the other side, I want to optimize for lower hardware. I said, let's use a single decoder. Every logical qubit accesses the same decoder. Well, now there's a bigger problem. While this is very optimized for hardware usage, the big challenge is that now you can face timeout issues where you're basically operating on a very small window of time. Some logical qubits may miss out correcting their errors because it's not able to access the single decoder. It's just waiting, and then timeout happens. So this is the other end of the spectrum where you use the least hardware, but then it has some implications on the decoding accuracy or capability.
What if we use, for example, half the number of decoders?
Half?
Yes. Do you have some problem?
That's what I come up with. Oh, yeah. But yeah, the key insight was that your decoder will not be able to correct all errors, right? You still have some logical error rate. So some events your decoders cannot correct. As long as your timeout errors are lower than that, you are fine. So we came up with this conjoint decoder architecture, which is slightly more tricky than the half sharing. But the key takeaway is that you make contention-aware sharing. If you have very frequently used resources, then you don't share them, but otherwise you share them. And that's what led to the conjoint decoder architecture, or the CDA. And the key idea was that you reduce hardware cost, but you still don't impact the accuracy a lot. And with the restricted sharing of hardware, CDA actually allows you to have negligible impact on the accuracy. So yes, it was right. And this is some performance number, but I'm not going to very specific details, but effectively it's very accurate, and accurate in the sense, okay, I'll talk briefly. For instance, if you have a distance 11 code, and let's say your physical error rate is 10 to the power minus 3, your logical error rate was something about 10 to the power minus 11, I think. So it's accurate. It's able to suppress those errors exponentially. The second thing was about the decoder latency. The decoding latency depends on the error event. You can't assign a single number to a decoder latency. And it was fast, actually. And then we could decode within the cycle time, which was a more futuristic estimate of 400 nanoseconds. The events you see in red are the events that lead to timeout failures. This is for a distance 11 code, by the way. And what we see is that it appears with less than probability of 10 to the power minus 10, which is lower than the logical error rate. And then for this decoder with distance 11, the configuration, we were able to get about 70% improvement in the memory reduction. There are some scaling numbers in the paper that you can look at. And then overall, the takeaway was that, yes, AFS is really accurate, fast, and scalable. That brings me to the conclusion. Hardware errors is one of the biggest challenges in quantum computing. It limits us from running most practical quantum applications today. And in the NISK era, or the near-term quantum computing, you will be running few domain-specific applications where you still outperform, hopefully, your most best-known classical algorithm. And in those cases, you don't really have the luxury or the resources to do quantum error correction. So you use software error mitigation techniques. So if your software is more intelligent, you can suppress errors better. And then eventually you want to build fault-tolerant quantum computers. So you want to understand quantum error correction today on these small systems, and you want to build and system-level solutions can help us build those error correction frameworks that you need to build fault-tolerant systems. Thank you, and I will be happy to take more and more questions.
So,
I hope I have excited people about quantum computing at least, and I'm very glad I got a lot of questions. It was a very interactive crowd. I really enjoyed it.
You're excited and not excited.
It's a quantum state, so that's good. Yeah.
So my question is, the error corrections, the main problem that we don't have more sophisticated error correction is the fact that they cost in general performance or any other thing.
In terms of,
Yeah, what's the cost to have more sophisticated error correction?
so the most sophisticated decoding algorithm for surface codes, for instance, is minimum weight perfect matching. And the best known implementation still doesn't complete on time. Imagine you are solving a graph matching problem in 3D with 25 layers on top, and then probably few thousands of nodes in each layer, and you're trying to match perfectly on that graph. That's the best possible algorithm. It's just not possible to solve it in real time in most cases. The worst case latency is very high. If you use software, yes, you can't decode in time, so you can't basically correct your errors on time.
So Poulami, thank you very much for all the background and also your research work that you explained in so much detail. So my question is that where do you see or envision quantum computing, let's say, in the next few decades? And to enable that vision, let's say, what are the key directions or research directions that kind of like need to be paved or problems that need to be tackled? So we talked about, let's say, error correction and fault tolerance in detail today, but what are other avenues, or like the most burning problems that need to be solved?
So I think quantum computing as a computing paradigm itself needs full stack solutions. Think about going from one generation of general purpose processors to another generation. You get some amount of performance from your transistors, which still hopefully is holding true. Some amount from your architecture, some amount from your compilers, and so on, right? So that is the kind of improvement I hope exists even in the quantum setting, where you are building devices that continue to be better and scale better. You're building these softwares which are smarter. You're building architecture that can support these large scale systems. You know, how you control things inside a fridge or outside a fridge. And these things differ based on the type of device technology that you choose versus, and the type of algorithms that you're trying to run. So I think definitely it's a very exciting time. And in the next few years, I hope there'll be demonstrations which is not just beyond classical experiments, but real applications that we can actually see that are being solved by quantum computers in the NISQ era. There are already some demonstrations in quantum error correction, where they have demonstrated codes, and I hope those scale up. And definitely, I think one thing we need to think about is also what are the challenges in different regimes of quantum computing. For instance, decoding for distance 3 is different from decoding at distance 5 or at distance 9. And then what are the challenges? What can we do in the cheapest way? So one of the things that I want to mention is that AFS was actually written before LILLIPUT. Yes, and when I went to Google for my internship, and the takeaway was that we don't really want to, or at least need to build silicon ASICs. We are not at that phase yet. We are building one quantum computer or two of them, and we are trying to sort of build these systems, and we are trying to still understand error correction, and then it becomes very cost ineffective solution, right? So that has also led me to reconsider or come up with better solutions beyond LILLIPUT, which I said I'm probably actively or maybe working on other things. So I think those are interesting challenges in the next few years. You also want to understand how to design better control infrastructure and see what you can do. The technology basically is an open problem, and then you're kind of building systems around that, and each of them has their own challenges. The things that work for superconducting devices may or may not hold true for CMOS and vice versa. So a lot of open problems. Yeah.
So if we assume we solve all the problems, right? We mentioned here a number of the problems in quantum computing. Seems like they have the perfect quantum computing as people envision today. Will there any room for us to compute?
Yes, why not? Cloud will still be probably there, and there will be newer paradigms, because one of the things you have to think about it this way is that quantum can accelerate a certain class of applications. It's not a replacement for your general purpose machines. We have GPUs today, but we still have general purpose machines, right? That's the same thing. We can think of the quantum as an accelerator for workloads that are fundamentally different, that people care about a lot. If you solve, let's say, carbon capture or nitrogen fixation problems, that's great. But then that doesn't take away that, you still want to solve machine learning or other types of streaming, all those kinds of problems. Yes. Yes.
So basically you're saying that we won't have portable quantum computers or quantum machines, something like that, because this is what you're trying to assume, right? You can have quantum computers that you give them.
So one of the biggest challenges with quantum computers is exactly that. And in fact, that's what led us to my first paper. It's on multi-programming. And what happened is that you have these large machines, and I was seeing that there are long queues. And then basically many of the times, even if IBM provided a 16-qubit device at that time, you are not able to access all 16 qubits. So multi-program them, increase your utilization. And that has led to a lot of work in how cloud providers should manage these hardware devices. How do they manage the queues and how do they prioritize users? And it's because you will not have like billions of laptops, but you will have a few of quantum computers. What do you mean by that?
Multi-tenant, let's say like 16 qubit system is existing as one system, but then two users have somewhat, let's say, separability of 8 qubits to me and 8 qubits to someone.
So at some point, Rigetti was allowing you to reserve lattices, 8-bit lattices, or 8-qubit lattices only. You could probably reserve two at the same time. I think you can actually use that kind of structure to sort of overlap your calibration experiments with user data, user experiments. So, yeah.
What about, let's say, the security implications of such a scenario, so like all the interference and stuff?
No. Actually, this is a very good question, because there are papers that actually told that if you multi-program.
The first question that pops up in everyone's mind in multi-tenant system, how faithful this separation is. I mean, we can barely compute using this device. Give them a break. But yeah, I'm just kidding.
Yeah, there was a work actually that followed up saying that you can actually have crosstalk. And if you are smart enough, you can learn from that crosstalk to know what's going on in the other application.
How do you work around it? How do you defend against such issues?
I need to work on it. I still don't see it as a problem yet, but hopefully we reach that problem. I know I'm aware of a work that uses homomorphic encryption to solve that problem.
Keywords. Every keyword is saying. No. Blockchain.
I thought we were talking about
I'm not telling that. I still want my job.
Is there any chance that homomorphic encryption does at all scale better with quantum computing?
Sorry.
Is there any chance that homomorphic encryption scales a little bit more reasonably in the quantum computer somehow, or why is it being considered?
I have no idea. Partly because I think it's not a thing that people have studied yet.
I think the partial reason might be also that homomorphic encryption is still based on the fundamental ideas of prime factorization and stuff. What?
Not sure.
I'm also not completely sure, but then if the key building blocks are not defendable against quantum, let's say, execution, then that paradigm itself might not be secure.
Yeah, but I mean, if you can come up with a certain elliptic curves, I think that's right. Elliptic curves, quantum safe, is that correct?
Sorry.
Elliptic curve cryptography is
Like the quantum safe.
So they are trying to sort of come up with those lattice-based quantum safe cryptographic protocols. Yes.
Also, they can
Yeah. There was, yeah. There's a very nice session on that last week I attended at Heidelberg Forum. It was great. Yeah. I think IBM and a couple of other people have worked on it.
Is there any possibility of have a hybrid system between classical and quantum computing?
So a lot of NISK applications, you actually use both. The NISK applications like quantum QAOA, quantum approximate optimization algorithm, or VQE, as I mentioned briefly earlier, right? That you sort of build this parametric circuit and you're trying to tweak the circuit parameters using a classical optimizer. So you run something, and that's why they are suited for NISK devices, because they can, you sort of think of it as doing gradient descent on a noisy landscape. You can still sort of do fine. And that's what those machines do. Are we still recording?
Yes.
Okay. I'm checking for question.
Yeah, so there's no questions on Zoom.
So actually, you should check.
Yeah, there is. Okay, are there other questions from our crowd?
So we can chat offline, group
Yeah.
meeting,
So,
whatever.
Can now maybe close the meeting and then we can meet also with Poulami.
So maybe I can say some goodbye remarks. So yeah, thank you everyone for watching and joining us and all the questions. And yeah, more importantly, thank you very much
Thank you.
for all
It
your
was a great
description
pleasure
and
to be
everything.
here.
Yeah.
Thank you. I really love the questions.
Okay.
Thank you. Should I stop sharing?
Is there a Zoom thing, where you close also the Zoom?